Middle of the screen? No. Okay. Yeah. Can you see this laser pointer thing? Yeah. Good. Okay. Excellent.
I can see the mouse for what it's worth.
Oh, okay.
Yeah. So is this the mouse? This orange red thing moving on top of your name?
Mm-hmm. Yep.
Okay, that's
great. Yeah, it seems to be working now. It was my problem, actually. Cool. Do you want me to unshare it and reshare it later, or just leave it up?
What's that?
Do you want me to just leave the share up, or?
Yeah,
or
yes.
Okay, I'll just leave it up.
We don't have an Australian background today. I'm sorry, I forgot.
What's up?
You're from Melbourne?
Sydney.
Sydney.
So let's wait like a couple minutes for people to show up, and then we can start.
Oh yeah, how long do you want me to go for?
So we have you can go for an hour and a half. You can stop early if you finish your slides. Yeah, feel free to take your time.
Cool. It should be fine. I don't know. You always think you'll finish in like an hour, but it doesn't usually happen, does it?
Right. Yeah. Most people are like, the seminar is an hour and a half. I only have an hour of slides, and then they easily fill an hour and a half. Well, I think we can begin. Great, thanks, Stephen. So welcome everyone to the CMSA Quantum Matter seminar. Today we're very happy to have Dominic Williamson from Stanford University. He's here to tell us about Oneform SPTs, topological measurement-based quantum computation. So thanks a lot, Dominic.
Great. Yeah, thanks for inviting me. I really like these seminars, although usually I have to watch them on video record later because I'm too lazy to get up in time on the West Coast. But hopefully this time works for everyone. I guess it works for everyone who's here at least. So thanks for coming. Great. So the thing I wanted to talk about was some connection between this class of one-form SPT phases that have had a bit of interest lately and some kind of model for quantum computation that I think is pretty cool. And I think it's really cool that some companies actually trying to basically, build a quantum computer with this method. But again, I'm not really going to talk about that, but okay, it's maybe a good motivation to look more into what we can do with different models in this setting. And I want to tell you about the connection between this one-form SPT classification of phases and how this topological MBQC works. So this is kind of, well, some work, I sort of started some part of this with Meng a few years ago and then put it aside. But recently I had this paper with Sam Roberts from PsyQuantum about some portion of these ideas, like for a specific example. And now I guess we're kind of exploring it more generally. Cool. So let me tell you about what I'm going to tell you. So hopefully I'll cover a kind of classification of one-form SPTs via the domain walls. So I'm not really going to claim this is like a new classification or anything, just some certain point of view on an existing classification probably. But it's a point of view that I like, and I think it's useful for making the connection to the MBQC. And then I'll cover how, from this point of view, you get to the way that symmetries act on the boundary and what boundary phases you get. And then once that's established, I think we can explain the topological measurement-based quantum computing with these states and phases. And okay, a cool thing about these phases is with the symmetry, they survive to finite temperature. And I'll explain that. And then basically, because of this reason, more or less, that and some symmetry constraints on the boundary, if you actually enforce the symmetry, you get something like self-correction on the boundary at finite temperature, which is kind of cool. I don't know if this will ever be useful because you need to enforce the symmetry, but it's kind of a nice result. And this also, I'm not saying that like I've come up with this. This has been shown in some previous works with specific examples. So previous work by Sam and then a recent work by Nankishore for 3 fermion. And then if I get to it, I'll also talk about gauging the symmetry of these SPTs and kind of what this does to the boundary and how you can use this to find realizations of all the SPTs in lattice models, basically. Cool.
Excuse me, Dominic, just make sure. Maybe you already mentioned, is the one-form symmetry here strictly X locally on the link, one simplex? Yeah. So I think maybe there'll be, I probably should be careful about exactly what I mean by one-form symmetry. I think I'll mention that later, but I think it's something kind of like Wen's definition of it. So it's just some operator that will act on like a codimension 1 surface through the lattice. I always have like a lattice in mind, and it's just going to act like a tensor product of exactly the same, like, there's some on-site group or on-link group, and it's always going to be abelian, right? And I have one representation of it that's like a linear rep, not a projective rep. And when this manifold that I'm codimension 1 manifold hits the state, it's just going to act on these links through this group rep tensor product of this. So will your Hilbert space construct on the site or also on the link, both sites and links?
Probably just links in the actual lattice models I'll show.
Okay. Right.
Yeah, links or obligates, so dual links. Okay. I'll get to that there, and you can ask me again if it's not clear enough. But yeah, let me first give you some background on this story, which is like the connection between symmetry-protected topological phases and measurement-based quantum computing, which is actually pretty old at this point. I guess this predates like people calling these things symmetry-protected phases, but it doesn't actually predate the symmetry-protected phases, which came a lot longer before that. But anyway, the simplest example to see this in is like a 1 plus 1D, but I'm going to use like condensed meta kind of notation and just call things by the space dimension. So 1D spin chain. And I think the simplest SPT model is this cluster state Hamiltonian. So you have a line of qubits. I've indexed them by some position V, and then we have the C2 times E2 symmetry. So actually a site is consisting of an even and an odd position. And then the symmetry acts on site with this grouping, and it's just like X on the left qubit on X on all the right qubits. Great. And this Hamiltonian is pretty simply related to the trivial Hamiltonian via this local unitary circuit that preserves the symmetry overall, but not locally. So this doesn't mean that you're in the trivial phase when you have this cluster Hamiltonian. But by using this circuit, you see that the ground state of this thing is pretty simple. It's just related to the ground state of the trivial Hamiltonian by this unitary. And then we're going to use this ground state to see how you use this phase for as a computational wire, basically. So you can use it to simulate a single qubit. And this is my picture for the trivial state. So I have this tensor diagram with these little dots and upward facing legs, meaning these plus states, basically. You apply this circuit. So my picture for the CZ is like this little box between 2 dots. And you apply this on all the links. So this is the ground state of your cluster state Hamiltonian. And then the idea is you measure basically in the symmetry basis. So my picture for, to say to a projective measurement, I'm going to be left, I'm going to project out all the spins I measure onto this either plus or minus state, which I'm representing by this plus state with a possible Z applied to it. And I'm going to measure all the spins except the 2 boundary ones, because I want to be left with something to talk about. Okay, so if I do this, I'll get some measurement results. I don't control these coefficients. They're like the outcome of a measurement. A1 through N and B1 through N. And now what I have left on the ends, if you just kind of rework the tensors, is this maximally entangled state up to some Pauli operators. So there's an X and a Z that depend on the coefficients I measured. And there's this Hadamard matrix, which I didn't define. It doesn't really matter. It's just some 2x2 matrix unitary. So people kind of came up with the name for this. They called it like localizable entanglement, which is the concept of like if you kind of measure out some region of spins, like how much entanglement, or, can you create a bell pair basically at the boundary of this thing, this region of spins you measure out. And this is kind of a proxy for being able to do some gate basically with the spin chain. You can kind of think of turning one of these, kets into a bra, and this is basically telling you that you can do this Pauli times Hadamard gate. So I'm going to kind of freely move, just use this ability to prepare like maximally entangled states as interchangeable with implementing these gates. But if you like, you could kind of do some teleportation on the left to teleport your qubit to the right up to applying this gate. So this is essentially, being able to do this is the same thing as being able to you basically simulate a qubit through this spin chain via measurements up to applying these gates. Okay, and the thing I'm not going to tell you is, okay, first thing, next slide, is that this ability to like do this Hadamard gate basically up to some Pauli correction is a property of the whole phase. It's not like dependent on this one state representative of the phase, of the SPT phase. So as long as you preserve the symmetry, anywhere you go in the phase, this procedure will still work. You might have to deal with like some coarse graining and exponential tails. They won't be quite as neat as I showed you, but you can show that it still works. And there's some references to doing that. And the other thing I didn't show you is if you can actually change the way you measure and you can get any single qubit gate you like, not just this Hadamard gate. So on this, basically the story is in these 1D phases, you can do whatever single qubit gate you like, or actually there's also a version of this for qubits and like pairs of qubits if you like. But the basic story is for a single qubit, you can use these certain SPT phases to do whatever one qubit gate you like via measurements.
Can I ask a question?
Yeah, please.
So the A and the B you get depend on the outcome of this measurement.
Mm-hmm. Yep.
But the Hadamard gate does not?
It doesn't. It actually just depends on an even odd effect. But if you kind of coarse grain your sites, then you'll always have the Hadamard if you kind of go one side at a time. So like there's going to be some gate that will be sort of native or something like that to your phase that you'll kind of get usually by just kind of doing the measurement in symmetry basis. And then if you want to get like different gates, you have to measure not quite in the symmetry basis. And then you always get these Pauli fractions. Yeah.
So how would you get something other than Hadamard? You would do a measurement.
Yeah, I think you have to basically measure in like, you take some plane like the XZ plane and you rotate in this plane, and then you can do other gates that, yeah, I should have a slide in this, but I kind of didn't because I'm not really going to talk about doing arbitrary gates. I'm just going to talk about this ability to do the identity gate or, some Hadamard gate in the rest of the talk. And the point you bring up is very good because it actually, use the stuff you want to be able to do whatever gate you like. So it's important how you do those. But let's say the stuff I'm going to talk about here, is kind of like 0th order step. So in previous stories, you kind of proved first you could do the identity gate, just like propagate qubits without doing anything, or maybe just doing some trivial gate like Hadamard. And then you would later on sort of see how you would protect doing some universal gate set. And it's an important issue. But it's kind of a bit special to, well, when we're going to get to the topological phases, it's going to be special to whatever phase you pick. Like you can't use the same method for all phases. So the blanket statements will be about this, just doing the identity gate, basically.
I see, thanks.
Yeah, and please, I guess the audience here is probably not super quantum computing, so if there's any questions that you might think are obvious, please ask them. So I wouldn't expect everyone to know all this background. Cool.
Dominic, I don't know if you were about to say this, but how is this related to the 1D SPT? Maybe you said it and I missed the connection.
Mm-hmm. I didn't really explain that, but the connection is basically because some signature property of the 1D SPT, or why does it protect this, is that you have these like degenerate edge modes, and as long as you're in the SPT phase, that they persist up to some exponential tails. And then you can kind of show that if you, well, at least for the measurements in the symmetry basis, you kind of measure out these sites. It just like exactly propagates this edge mode along the chain. So if you want to think about, instead of just preparing a maximally entangled state, actually propagating one qubit along the chain, which is kind of what you would do to do computation. These are kind of equivalent, but if you imagine this point of view, then the connection is because of this this edge mode existing, basically.
I see. And could one also rephrase it by saying that the state you start from, this basically a product state, right, with a rotated basis, in order to convert it in order to convert it to the state that displayed here with non-trivial edge state, you have to act with, you could think of it as a sort of finite depth circuit, but it's, the length of it to the extent is non-local, it spans the entire system. Is that correct?
Yeah, it's definitely important that the whole, pairwise, every pair of qubits is like entangled along the chain. And you kind of need that to be, in some sense, like maximally entangled, or at least that's why this definition of localizable entanglement was made. Like if you, by making measurements, can localize in a maximally entangled pair, you kind of need that property. If you don't have that property, you're not going to be able to just do the identity gate via measurements. So it's important that the circuit you do is entangling enough, right? And there's no breaks. If there was some break in the circuit, this wouldn't be useful. Okay, should I go to the next slide?
Does this recovering procedure depend on like knowing where you are in the phase?
Yeah, I think if you, which one do you mean? Do you mean like if you're doing kind of arbitrary gates or just kind of doing this trivial gate?
Just a trivial gate. Suppose you've measured everything already and you want to recover the qubit on the state on the other side. Do you need to know what?
Yeah, I think you do need to worry about having these exponential tails, but more or less, I think having the operator you do, if you're doing this just this symmetry basis thing, it shouldn't really matter which point you are at in the phase. This should be like a property of the way the symmetry acts. But if you're trying to do the other gates that are not kind of in the symmetry basis, you have to be a lot more careful. I think one of these papers explains that carefully. You kind of need to make sure you get some error when you do like a non-symmetry basis measurement, and you have to like kind of make sure you suppress these errors enough when you're away from the fixed point. So it is important you do things carefully when you're away from the fixed point.
So you always get an entangled state between the edges. It's just the precise nature of that entangled state will differ based on where you are in the phase, but it'll always be a maximally entangled state as long as you're inside the phase.
Yeah, I guess that's my worry. That how do you know what the nature of the entanglement is, or arbitrary like point in the phase? But I guess you said that there's a recovery procedure that depends.
Yeah, sorry, I think for just preparing this like maximally entangled state, you can just keep using the same symmetry basis, because I think you basically assume that symmetry doesn't change. And then like exactly in Dominic's paper, I think it's explained, like proved basically using MPS techniques that you will exactly get this maximally entangled state between the ends if you measure it in the symmetry basis. So you can kind of prove it, I guess, and it's not super obvious naively. I think that's this reference here.
I have a further question. I'm asking for maybe quantum field theorists. This might be a dumb question, but can you translate what you say to maybe continuum field theory statement, which might be helpful for people like Nati and others?
I'm not sure exactly how to do that, but maybe there's a similar version.
What it's worth, Nati doesn't need this help.
Okay. Yeah, or maybe I can take another stab at the previous question. An easy way to see why.
Help Druven by saying that I think you discussed a 1 + 1 dimensional SPT phase with an anomaly in the Z2 times Z2.
On the boundary, there's an anomaly, yeah.
Which gives an anomaly in the boundary theory that corresponds to it. I hope helped quantum field theories from Druven.
Thanks for the translation. It's really nice.
I think I have a better answer to Nat's question, actually, to see easily why you get this boundary entanglement at a high level. So you have like the symmetry actions. I should have drawn a picture of this, but you have the symmetry actions in the bulk of the chain. And if you believe that they act on the boundaries via some projective rep, which should be basically, I don't know, some way the defining property of the SPT phase, then you have like the symmetry action in the bulk is equivalent to these projective rep action on the left and right boundary, and say that's in tensor product factorization. Then if you measure out this symmetry in the symmetry basis along the bulk, basically all these X actions in the bulk will become just plus or minus 1, right? So now you're just left with these edge modes, and you have like perfect correlation between the projective rep operators acting on the left and right edge mode up to this plus or minus 1. And this basically shows that you have a bell pair. Having these stabilizers tells you what state you have of the boundary spins, and if it's sort of perfectly correlated like this up to the plus and minus 1s, that just tells you it's a bell pair, it's maximally entangled. Okay, so, and I'm going to use that kind of reasoning for the topological case later. Great. So then we go to 2D. So this was just doing like simulating a single qubit. If you actually want to do some interesting computation, or some computation has a chance of being universal and sort of unsimulable classically, you need to have more wires. And there's some nice, you can do this with a bunch of 1D chains, or you can go to 2D, which is kind of more natural. But in 2D, I think there is some work on using just the global symmetry SPT, but I think the story is nicer for thinking about these things called subsystem symmetries, which I don't want to get too much into because it's not going to be important at all for the rest of the talk, but there's kind of a nice connection generalizing the 1D story if you consider 2D subsystem symmetry-protected phases, protecting some ground states. So in this case, I'm just going to consider the 2D cluster state, and this is protected by some linear subsystem symmetries, just doing spin flips along diagonals in this case. Okay, and then there's like a slightly more complicated, there's an extra step beyond the 1D stuff. So you have some choice of different bases to measure in. So if you just measure in the symmetry basis again, that's going to do a similar thing to before. But if you measure in this different basis, the Z basis, it happens to just totally decouple things. So if you make this pattern of measurements, what you're left with is actually controlled Z gate. If you kind of do the tensor manipulations, so I'm thinking of simulating these spins running across the lattice, then this X basis measurements can be used to prepare basically a control Z gate between these spin chains that I'm going to simulate qubits on. So this basically gives you an entangling gate. And then if you believe me before that I can do arbitrary single qubit gates, I can simulate these on the wires, this is enough to give you universal computation. Okay.
Dominic, can I ask a quick question about this?
Yeah, please.
So actually 2 questions about if you actually go back the same slide, but the previous, yeah, thank you. So the first question is, so here this action X measurement is not along the symmetry direction, it seems. And secondly, it seemed important, like the way you explained the 1D case, right? So you nicely explained how projecting into the symmetry basis kind of keeps things nice, because it's just essentially kind of projecting onto the symmetry quantum number in the bulk, and you're just left with the fractionized symmetry at the edge. But so here you're also involved, here you're also measuring in the Z basis. Is it correct to say that that actually depends in a fine-tuned way on the precise Hamiltonian, and it would depend then if you're not in a fixed point limit, whereas the X measurement doesn't depend on that?
I think you're probably right. The way you actually establish the connection between the SSBT and the MBQC as a phase property is actually you kind of just do a quasi 1D thing. You just put it onto a cylinder, and then you want to have like your symmetries basically running along the cylinder. So you can, like you pointed out, the diagonal direction would be more natural from the point of view of the symmetries. Well, actually, yeah, okay. I think the direction I've shown actually is the way you do it. But basically, you want to just compactify this thing, and then you'll have some big group on the cylinder. And then you kind of just show that by propagating, you don't actually, I don't think, need to measure out these Z basis things. This just makes the picture of how it maps to a circuit a lot clearer. But you actually just look at what evolutions you can act on this chain going from one side to the next using symmetry basis stuff. And then so yeah, I think the way I've shown it is a bit different to actually how you establish the connection. So I think it would basically, doing these decoupling measurements would depend exactly on how you realize the state in the phase.
There's more than one kind of subsystem symmetry in this system. So there is a different subsystem symmetry that would protect this kind of protocol. Whereas if you did it down the diagonal direction, that's what would be protected by just the X's along the diagonal. So
oh, I see. So there's also a Z symmetry, or
Well, the subsystem protects this one is a bit complicated. It's like has X's in some places and Z's in some other places.
I see. Okay.
Mm-hmm.
Yeah. Thank both of you.
Yeah, I think I actually have the reference you want to read to understand this more complicated subsystem symmetry. Okay, great. Right, and that one of these references should be the one you want. Maybe it's the 2012 one.
Thanks.
And then I think this 2018 one is about doing the one that uses the diagonal symmetries, that protocol. Okay, cool. And okay, so you can basically show that the gates you can do in this cylinder layout are protected throughout the subsystem SPT phase. So that the latter paper is the one I'm thinking of for that, in a similar way as the single qubit wires were protected in 1D. Okay, so this is really cool, but then the problem is you want to add error correction to this. So one thing you could try and do is kind of also simulate the error correction, but a much nicer idea that came a while ago was to use some sort of topological protection. And this kind of requires you to add another dimension. So now I want to think about the 3D cluster state as the simplest example, but I'm thinking about the particular one where you have qubits on faces and edges of a cubic lattice, and you have these 5 body terms, so they act on like a face and the surrounding edges, or an edge and the surrounding faces. I didn't draw that one, but it ends up being related to these ones by just doing like a lattice to dual lattice translation. Okay, so this is a model. And this thing ends up having a Z2 times Z2 one-form symmetry. So if you take the product of these plaquettes over a cube, for example, you get just some X's acting on the surface. And you get some dual thing of edges touching a vertex, product of X's also being in symmetry. And these kind of generate your Z2 times Z2, one Z2 living on the plaquettes and one on the edges. And the state has this symmetry. And it's the one you want to consider for the properties of the phase that we're going to talk about. Okay. So I think the first thing is you ask how this one-form symmetry acts on the boundary. In this case, the symmetric boundary basically has a toric code living there. So I didn't actually show the boundary Hamiltonian, but you truncate these Hamiltonian terms in some way. Hopefully you believe me. There ends up being essentially a toric code living there, but it's sort of coupled to the bulk by having to be symmetric under this determination of the bulk symmetry. But you have these string operators of the toric code along the boundary. So you have like the M string operator and the E string operator, and they correspond, one corresponds to one Z2 and the other to the other Z2 from the bulk. And right, in this picture I'm showing, if you have this sort of symmetry action on this ground state, then it's equivalent. So when acting on the ground state, it's equivalent to acting on the boundary with just these M string operators, one of the generators on this plane. Okay, and you also have the other one, which is equivalent to this E string operator. So if you kind of isolate a single boundary, you can have like this projective rep of these string operators when they cross in the right way, which is going to show you that there's some degeneracy on the boundary, but actually it's topological because it's encoded in the ground state of this toric code, not just in like a single standalone qubit.
So just to be clear, by one-form symmetry, you mean here a symmetry that acts on two-dimensional surfaces in 3D, right?
Mm-hmm. Yep.
And it can act on any two-dimensional surface. It doesn't have to be flat or anything.
Yep, that's true.
And often part of the definition of one-form symmetry would be that the symmetry operator for two surfaces that are, homotopic or can be deformed into each other is the same operator. But it seems like here that's probably not the case. Is that right? Yeah,
I think I'm definitely not using the same one-form symmetry in the same way. Maybe I shouldn't call it this. I think I'm using it more in the sense of like this when has some definition in a paper, which I put a reference in somewhere that doesn't seem to be on this slide. But basically, I'm just saying it's some operator acting on these surfaces, and it should act via the same on-site matrix. So if I draw the surface in a different way, every site it hits, right, it just acts via this particular choice of on-site representation. That's linear.
Sorry, Dominic, could you say it again? What is exactly the one-form symmetry? I mean, well, how do you define it such that it acts only on a surface? It's written as a P belongs to the boundary of the cube, so it acts what on like 8 links?
Yeah, so
12. No, well, yeah. How should I think about the 6 faces of the cube or the 12 edges?
Yeah, maybe the confusion is more that I might have used one-form differently to how I meant to use it. But I could say it this way, that if I just take these generators of the symmetry, like the left one and all all boundaries of cubes, that generates some symmetry group. And I'm going to call that a Z2 one-form symmetry. And similarly, these edges touching a vertex, product of those x's, and if I take products of these generators, I'll get some other Z2 symmetry. Basically, on the full lattice, it's going to be some huge Z2 times Z2 times Z2 group. But I want to think of all that as as part of the same symmetry. So that's how I want to define it.
What is the second operator? You multiply all the x's on the links touching a particular vertex?
Yes.
So it does not act on codimension 1 in space. It acts at a point.
Yeah, if you think of the dual lattice, it's just the faces of the cube again.
Well, the question is whether this is an extended thing or it acts locally.
Oh yeah, if you think of the dual lattice, it's just the faces of the cube again. So when you product them up, it's going to be the faces of the big surface you generate. Okay. And it won't leave anything in the interior.
Okay, but then I'm still not clear on the answer to the questions you were asked before. If you deform the surface slightly, does the answer change or not? If you don't cross any operator?
If you're in the ground state, no, they all have value +1.
That doesn't answer the question. These operators on the ground states, all of them are 1. So I would say that the symmetry just doesn't act on the ground state.
Well, the symmetry is acting in some non-trivial way on the Hilbert space, and the ground state is just symmetric.
Okay, so it does not act on the ground state, it acts on excited states.
Yes, yep.
Now
exactly what we'll talk about.
Excited states or operators. If we deform the surface slightly, does the answer change or not? Imagine I just put operators, compute vacuum expectation values of some operators, perhaps lines, and I'm asking whether deforming the surface a little bit, not crossing anything else, whether it will change the correlation function or not.
It won't. Yep.
It will not.
It will only depend on some topological linking, exactly. So if you change that, the answer could change, but without changing that, it won't.
Wait, sorry, that doesn't
sound
right.
In response to Dominic's question, you gave the opposite answer. He asked you whether it depends only on the homotopy class of the surface, and I think the answer you said was no.
The exact operator you write down will be different, but the way it acts on some excited state will only depend on this.
No, I think that's the same statement. If the operator is different, then there must be states on which it acts differently, right? Otherwise, it would be the same operator.
Yeah, there are states that it acts differently on, but I guess if you fix a configuration of some excitations, right, then it should only depend basically on how the operator crosses things, how it acts.
Yeah, but you get a minus sign. At least you get for a given eigenstate, you'll get a minus sign as you move the operator around, right?
Yeah, that's true. You could always put like a Z operator on any given plaquette, and then this symmetry will see a minus sign if it hits that plaquette. So you can find, I guess you can find states such that it acts differently in every position. I don't know. I think, well, this definition of what the symmetry is pretty concrete. Maybe what to call it. Maybe I shouldn't call it one form. I don't know.
Well, no, it's very important actually to call it correctly because not for the terminology, but when you want to say that there is some kind of an anomaly in that symmetry, if you want to classify the anomaly correctly, you need to understand exactly what the symmetry is.
Yeah, well, I think, well, maybe I shouldn't call it one form, but these are going to be symmetries. They're going to act on products basically of codimension 1 surfaces.
We can call it phaseful one form symmetry, right? Because it doesn't just depend on the homology class of the codimension 1 submanifolds over the whole Hilbert space.
I extremely object to that terminology, but okay, I may not have that argument now.
So does anyone know what we should call this, or is there some name. I think Wen is just calling it like one SPT.
To be honest, I don't even see the surfaces, despite what you said, because the second operator acts at the point. So this is the codimension. In 3 dimensions, this is codimension 3. So the operator, the second operator, you pick a vertex and you multiply all the x's. This commutes with your Hamiltonian, I guess. Therefore, it's an operator that acts at the point. It's not active. It does not act on the surface.
Yeah, I think. Well, the way I was thinking
the thing about the one-form symmetries is that you have an operator associated with the surface, but it's not simply a product of symmetry operators acting at points.
I think
I know how to fix it, though.
Okay.
I think the way to fix it is to say that you are interested only in the ground state. And then these operators that you wrote are trivial. So you take a quotient of this huge symmetry group that you had by the operators that are trivial, and you're still left with non-trivial operators, which might be operators associated with surfaces. So I think that the clean way to think about it is to stay only in the ground state and to have defects. No excited states, only the ground state and defects. And then the might or might not be surface operators which act as one-form symmetries. This is what happens in the toric code, for instance. This is exactly what happens in the toric code. The analog of your operators here are the operators in the Hamiltonian of the toric code. You can think of them as being symmetries because they commute with the Hamiltonian, but this is not what the one-form symmetry is. The description of the one-form symmetry is what I said, namely you focus on the ground state, you throw away all the excited states, and you only consider defects. And then there is a one-form symmetry with line operators that generally. But I shouldn't slow your seminar. So
yeah, you already pre-predicted what I'm going to talk about later, which is exactly building defects on top of the ground state and how symmetries act there. So maybe the way you said it is exactly the way I want to say it. But I'm not sure what I should call this symmetry acting on the whole Hilbert space.
Well, for one thing, it's not a one-form symmetry.
Yeah, well, let me just already apologize because for the rest of the talk, I probably used exactly the same wrong terminology. But let's interpret it the way that he said, that this is just some huge symmetry group, and then on the ground state and the defects, it acts as a one-form symmetry. Hopefully that's true. And just the second point about this second symmetry, it's just, think of it as surfaces on the dual lattice. Because if you take a product of a bunch of points, it will only still act on like the surface in the dual lattice around those points. That's the sense in which it's acting on a surface. I know it looks like it's acting just around a point. Maybe that is an important point, that this is basically surfaces of the dual lattice. Otherwise, the things I'm going to say are not going to make sense. Okay. So you can take these symmetries acting on, yeah, let's get back to this slide, acting on some surfaces. And if you have a boundary here, and imagine some slabs, so I'll just do periodic boundary conditions on the XZ and YZ faces and have the XY face at the top and bottom open, then from the properties of the ground state, basically this action on the ground state is equivalent to these string operators in the boundary. Okay, and you can do this with the other generator for the E symmetry, and this gives you some projective rep on a single boundary, which corresponds to the string operators of toric code, basically, on the boundary. So you end up getting 2 encoded qubits in this example. Great. So how, from this, do you see that you have some ability to do at least the identity gate in a topologically protected way? I'm going to use the same concept of this localizable entanglement, but now in a topological encoding. And essentially, if you take this symmetry basis, in this case, which is X, and you measure out some slab here, sites and edges implicates in X, you turn this like symmetry action inside the slab into just a plus or minus 1, given by the measurement result. This acts equivalently to this pair of M's at the boundary. And so in the state you've produced, you now have this stabilizer, basically, which is like a symmetry of the new state with the bulk slab measured out, which has this pair of M's as like a perfect symmetry, if you like. If you act with the M line on top and on bottom up to plus or minus 1, it's just going to be absorbed by the state. You can do the similar thing for the E strings. And together, this basically is telling you that for this, you have this topological qubit on the top and the bottom by making this new surface. And these guys are perfectly correlated like in the topological encoding, you'll have the state is stabilized by XX on top and bottom and ZZ on top and bottom. So this is how you see that you have this topological encoded localizable entanglement. And this lets you, well, this shows you that basically you can perform this just identity gate to propagate some topological qubit through the bulk. And it's been shown in, I think, these some of these references that will argue that to some extent this should persist throughout the one-form SPT phase. And that's the thing we want to kind of generalize, this idea. And the idea why it should persist throughout the one-form SPT phase is that the properties of these string operators on the boundary should be determined by the phase. And then the fact that you can sort of measure in the symmetry basis to produce this like maximally entangled pair at the boundaries is just going to be a property of the phase as long as you preserve the symmetry. Okay. So yeah, basically generalizing this to some wider class of models is the idea. Great. So the way I want to approach that and to actually give lattice models for everything is to use this Walker-Wang class of models, which I'll explain in a minute. But first, let me just say, for people who already know about these models a bit, how this example can embed into that understanding. So you can basically understand, well, you can exactly understand this previous cluster state model as just being, it's just a Walker-Wang model up to some lattice redefinition. And this should be kind of familiar. So in Walker-Wang models, we put in some anion theory into the model. And on the boundary, you basically get the anions of the theory you put in. So in this case, we got these toric code anions on the boundary. And I'm going to show you in a second that the model you're realizing these on is exactly just Walker-Wang applied to the toric code anions in the bulk. And the way to do this is actually just really, really dumb. You just you redefine the lattice by moving the plaquettes onto the edges. So you now have 2 qubits per edge. So this matches the Walker-Wang lattice. And then if you just look at what the Hamiltonian is, it's sort of on these new degrees of freedom. So I have 2 qubits per site. I'm using this notation that's telling you like which Pauli is acting on the left and the right qubit. This might not look super familiar, but this is exactly the Walker-Wang term you write down if you plug in the toric code anions. So this cluster state model was just realizing basically a special case of Walker-Wang model if you plug in toric code anions. Great. And then in this case, if you kind of product these plaquette operators around a vertex, you produce these symmetries, which was the one-form symmetries I showed before. Now they both live around vertices, but so in the dual lattice, they're living on some surface. Okay. Right. And so in the Walker-Wang way of understanding, we kind of relabel these basis states, it's just spin basis states, via some string operators. So the thing I put in was the toric code anion. So I have the vacuum sector, E, M, and psi. And then I just assign these to some basis states in this way will work. And then I can reinterpret exactly this one kind of plaquette term in terms of inserting a loop of this type, anion type E. And because of the non-trivial braiding of this theory, it'll produce these sort of sticking out Z operators as well as these flips on the edges you fuse it into. The other term comes from M, and together, if you product them, you'll get the psi term. And then this sort of one-form symmetry in this language is just telling you basically at the vertex that I need to satisfy the fusion constraints. So I just drew a few pictures of some configurations satisfying fusion constraints, but the term is just telling you basically that at this vertex, if I look in the ground state, sorry, in this space of symmetric things that satisfy this symmetry, it has to satisfy the fusion rule of this vertex. Okay, that's probably a good place to stop the questions. Oh no, sorry, I'll go 1 or 2 more slides.
Sorry, I do have a question.
Yes.
Just in case I don't want to get lost. But earlier you mentioned there's 2 type of kind of close to the surface operator, right?
Mm-hmm.
And then can you just express that 2 surface operator in that model you just showed, the torical Walker-Wang, maybe in the previous slide?
Yes. So sorry, that's
on the plaquette around the qubit, right? And this also turn around the vertex and then attach the links. So what are the operator written in this form?
Yes. So written in this way, it's surfaces living on the dual lattice, and because I moved the spins, they're both just surfaces living on the dual lattice. So if I draw some surface through the dual lattice, it's a collection of edges that go through the plaquettes of the surface. And then I apply basically xi or ix to these. That's the way this symmetry acts. And it will be generated by products of these things.
But this way of writing, it looks more like the second type of operators you will have, the links around the vertex.
Yeah, correct.
And the first one, the plaqué around the cube is C.
Yeah, I mean, if I just change my lattice, the reason I picked this lattice is because it exactly matches Walker-Wang. And in Walker-Wang, the symmetries are these things around vertices, but I could just redraw this whole picture with every edge being a face now on the dual lattice. And then these would look like just plaquettes of it on the face of a cube.
Okay.
So maybe it's best to think about them just in the dual lattice.
No problem, thank you. And should I think about this surface, this closed surfaces operator, or?
Yes, if I'm not thinking about having some boundary, then the things generated by these symmetries will all just be some closed surface operator. Yeah.
But once you have this tensor product of those operator around a surface, what would you get in the end? Just make sure we have the same surface operator.
I mean, if you draw some surface on the dual lattice, you get a collection of edges that it passes through, and then you just put ix or xi on all those edges.
Okay, but will they cancel out along the overlap links?
Oh, what do you mean? So if I take a product of like two vertices next to each other, they'll cancel on the link between. That's why if I take a product of stuff over the vertices interior to some ball, it'll just act on the surface, well, in the dual lattice. But
they do X also on the interior of the surfaces? Actually, they are wrong. Oh, I see. I think I see this picture. Okay. I think around the surface you span, maybe there will be some cancellation, but in the perpendicular direction, there is some leftover operators, right?
Yeah, if you take a product of a bunch of these, only at the boundary there's going to be operators. There would be nothing acting inside the.
Yeah, along the surface, there may be some cancellation, but the normal direction, there's still like the normal direction. There could be those IX operators.
Yes, exactly. I mean, if I look in the dual lattice, then it's like the surface of these cubes and just with Z2 stacking. So if I stack a bunch of cubes, then whatever faces are not canceled out up to Z2 will be left in this dual lattice.
Okay. Yeah. Okay. I can imagine the surface you were thinking. Thank you.
Yeah, sorry. I mean, it's a bit unfortunate. Everything is going to be in the dual lattice when I'm working this Walker-Wang picture, which will probably be for the rest of the talk.
Yeah. So I have a quick question.
Yes,
so there's another similar model, the 3-fermion Walker-Wang. So can we also take this model as the Z2 times Z2 one-form symmetry? But that model is originally proposed for the time reversal case. So what's the difference between these two models?
Oh, I guess, yeah, we have looked at the 3-fermion as like kind of a baby step, I guess, away from the story code example. And it has like basically, very similar properties. Like you said, you can think of having the same kind of symmetry, but the Hamiltonian's different. And you see this via the domain walls or the boundary action of the symmetry, which hopefully I'll explain in a minute. And then the relation to this time reversal global symmetry, I'm not thinking about adding global symmetries for the purposes of this talk. I'm not. It is an important issue. And then if you want to do interesting like topological computations that aren't just doing the identity gate, you definitely want to think about these global symmetries. But I'm basically not going to consider global symmetries in this talk. I'm just going to think about having the one-form symmetry to define the phases.
I see. But I think in the 3-fermion Walker-Wang, when we take the product of the plaqué operate, we actually get a 2-star operate.
Oh,
so
yeah,
in your case,
right.
Did you get a single or double in your model here?
No, you're right. That this property, that the product of these guys gives one of these stars is not important. So in the Hamiltonian for Walker-Wang, I mean, we include these as well in the Hamiltonian. In this case, they're redundant. They're not always redundant, as you pointed out. Well, I mean, yeah, if you write it this way, they're not always redundant. But if you just consider the Walker-Wang for 3-fermion, you can still think about these will still be symmetries of the Hamiltonian, and you can think about the domain walls they create and sort of play the same story as in this one. You just don't have this property. So this property here that I pointed out, that these products to give these, is not essential. So that's good to point out. And it won't be true in general for the models I'll talk about. Okay, so thinking about this as a Walker-Wang, this gives a kind of nice picture for the ground state, which gives you a nice way to understand I think it's a nice way to understand the topological MBQC. So the ground state of these Walker-Wang models, ignoring boundary conditions, is just basically a sum over all the closed anion diagrams you can write on these edges that satisfy the fusion, and it's weighted by this factor, which up to some multiple is just a phase for these abelian models like the toric code. And in this case, the phase is just given by some linking number between E and M strings. So you have to define this properly, you have to resolve the psi into E and M, but that's not very important for purposes of the talk. In general, you can think there's just some phase factor given by creating the anion diagram you have in this configuration from vacuum. Okay, so you get like a sum of these different configurations that are allowed, weighted by these phase factors. Cool.
Excuse me, naive question again.
Mm-hmm.
The reason you have your so-called this one form was this maybe I don't know how to use a quotation or this one form, the symmetry of the Z2 times Z2 is because you assign 2 qubits, which means the 2 to the 2-dimensional Hilbert space on the links.
Mm-hmm.
Is that right? Because the way you write the operator is also, you know, xi or ix
mm-hmm.
on the link. So that's tightly related to how you design the Hilbert space on the links, correct?
Yep.
So suppose I have maybe 3 qubits. Do I get maybe 3Z2?
It depends exactly what model you write down, but if you wrote down some Walker-Wang that was modular, that had a Hilbert space of 3 qubits and it was an abelian theory, then yes, you would, well, if it had the anions had the right fusion rule, you would get that symmetry. But I will say that about that in a second, the more general thing and what symmetries you get.
Yeah, okay. The way I look at the surface, it seems like that's the result. Okay, thanks.
Mm-hmm.
Can I make a quick comment, maybe / a question here? So if I understand correctly, I think the continuum limit of this setup is that in 3+1D, you have this Z2 cross Z2 one form SPT. And generally, on the boundary, the system will have some anomaly inflow by the SPT. And in the case we discussed, the anomalies between the two Z2 one form symmetry of the Z2 gauge theory in 2+1D, the low energy limit of the toric code. And as to Yuan's question earlier, one can instead consider the 3 fermion Walker-Wang, and then the low energy limit of the boundary theory will be the spin 8 at level 1 transassignment theory. That also has a Z2 cross Z2 one form symmetry, but with a different anomaly. And in the bulk, it's a different SPT that inflows a different anomaly.
Mm-hmm. Yep, I agree. I think I want to try and explain this from this point of view of these models, basically exactly how to see that and how you can see this, whatever the kind of anomaly that the SPT gives to the boundary from the way the domain walls behave in the bulk. And then when you push them to the boundary, there's some matching condition to basically anion, some string operators on the boundary, which should tell you exactly the braiding of the string operators. And so different SPTs tells you different braidings on the boundary, right, exactly like you said.
Yeah, because the anomalies of the boundary TQFT is captured by the braidings or by their spins. Okay, thanks.
Yep, I totally agree. I'll get to that from this point of view. Again, I'm not saying like I'm deriving this for the first time that there's some matching condition of one form SPTs to boundaries, but from this point of view, I'll explain it. Great. So just, I think the final thing I want to say about this Walker-Wang picture on toric code, the MBQC with this cluster state that has toric code at the boundary. I explained to you the ground state. And then if we want to think about what this measuring to propagate the identity gate does, in this case, when you measure, you're measuring in this string basis. So X in this case is just the basis of string labels. And so what you're left with is some history, basically, of where these string labels went. And so if there's no errors, like these will be closed allowed anion diagrams. And then it's possible you have some stuff ending on the surface of the Walker-Wang you're keeping. And these are just surface anions of the type, given by this string. If there are errors, so there's an interesting property of this because you get this history that makes it kind of fault tolerant. If there are some small enough rate of errors on the thing to begin with, then these anion histories can be broken apart. But you can actually correct this so long as the by just kind of repairing them up, so long as the error rate is low enough. So yeah, you can find some correction if this error rate is low enough. And then you use this kind of history. The idea is you can use this to, if you like, instead of just preparing some maximally entangled state, you can make sure you're doing the identity exactly, which corresponds to just finding the correction for these possible excitations you're left with on the boundary to restore them to the vacuum, yeah, without doing like a logical operator. So I don't want to accidentally go around this cycle when I pair these guys up. But if you have the history and you've corrected it, so it's like, the correction works, so you're not accidentally correcting in the wrong way, then you can do this by using the history information. So this is how you do the identity gate, basically by measuring out a whole bunch of stuff from the point of view of the Walker-Wang. Great. And then I think I'll get into some more general things now. So if there's any more questions about the Torah code example, I could take them. Otherwise, I'll move on. Okay, good. So I didn't actually tell you the definition of the Walker-Wang model. I just showed it for people who already knew. But to define this thing, I'm going to talk about the modular case, so like the non-degenerate anion theory case for now, and I'll specialize to abelian in a second. Later on, I'll mention the degenerate case in case someone wants to ask about that. I will talk about that later. But for the next, I don't know, 15 minutes, just non-degenerate case. Okay, so the basic data you put into this Walker-Wang model is some modular tensor category or anion theory. I'm going to specialize to abelian anions, but I'm just drawing everything for the general case because those figures already exist. So I'm using them. So yeah, this anion theory, the way I'm going to use it is specified by some finite set of anion labels and fusion space dimensions, which can be 0 to indicate that fusion's not allowed. For abelian anions, these are always just 0 or 1 dimensional to say that the fusion is allowed or not allowed. I'm going to have some associators between different orders of fusion, F symbols, and then there's going to be some braiding defined for these anions, given by these R symbols. They have to satisfy these consistency equations, so you can't just write down anything you like. And then I get this important gauge invariant data. There's more gauge invariant data than this in general, but for these abelian cases that I'm thinking about, this is definitely enough. There's this S matrix you get by considering this link and resolving this into a number. And then also you have the topological spin, which comes from twisting the anion, like ribbon operator. Okay, so for abelian anions, this simplifies a lot. The fusion and the anion labels are just given by some finite abelian group. It has to be abelian to be consistent with the braiding, allowing to swap things. Then if you specify the topological spins via some non-degenerate quadratic form, so I should have mentioned the degeneracy condition. We want this S matrix here for sort of any, we have some idea that if there's some property we like called remote detectability, that you can sort of detect some topological sector using topological braiding processes. If this is true, this S matrix should be non-degenerate. And then I think you can also argue that furthermore, it should be unitary if the system you're realizing this in is coming from a Hermitian Hamiltonian. So I'm going to focus on the case of these unitary S matrices, which are non-degenerate. So if we're looking at this case, the full theory, once you specify the finite group, is just given by this non-degenerate quadratic form. And there's a classification of these things. So you can use this to kind of write down your list of abelian theories up to equivalence. Yes, so given this Q, you can find some F symbol and braiding that will give you the way to compute things up to some gauge equivalence you don't care about physically. So the upshot is this quadratic form and the group determine everything, which is not the case for more general anion theories, but here is enough. So I'll label these abelian anion theories just by the abelian fusion group and this quadratic form going on. Okay, yes, and I'll mention what happens if you make a Q degenerate later on, and there is also a classification of these degenerate ones. So for the writing down the Walker-Wang model, conventionally we have to resolve this. So we want to write it on the edges of a cubic lattice. We have to resolve this vertex. Well, we don't have to, but it's convenient to actually use these fusion spaces and F and R moves to write down the Hamiltonian. For the abelian models, you don't actually have to do this, but I think it's still convenient to think this way. But what happens is that these edges inside, at least within the subspace where the fusion's satisfied, anything written on them can be rewritten on the outside. So that's something to keep in mind. I can write down all these lattice models just with no resolved vertex. But for the pictures, because they already exist with these resolved vertices, and I think they help to see more clearly how you would actually write down the Hamiltonian, I'm going to use this resolved lattice. Okay, so the Walker-Wang Hamiltonian has this form where you have these vertex terms and some plaquette terms, and they are commuting, and each one is projectors individually. The vertex term basically just looks at, so on the edges, you should imagine there's some string types, the labels coming from your anion theory. And the vertex term just says like, so for, I'm saying this in the case of abelian, I've written this in the case of abelian models, this NABC is just 0 or 1, telling you that this fusion can or cannot happen. So it's just putting energetically some constraint that you have to be in the space of allowed fusions on your edges. Now this plaquette term, which is summed over the anion types, which I've labeled by S here, acting on some plaquette, it basically just inserts some loop of this string type there on that plaquette. And then to get a matrix out of this, you resolve it into the lattice. So this is where the braiding comes in. You need some braiding information to kind of move these sticking up and sticking down edges out of the way. Once you do that, so this picks up some R symbols, and then you start fusing this thing in and moving it around the endpoint around the loop to come back to the start. Pick up a bunch of F symbols. You then resolve that little bubble back to a single line and move these guys back in for another few R symbols. And you get this kind of messy Hamiltonian term. I'm not going to bother writing down explicitly. I think you can find the explicit form here. But basically, the idea is you just fuse the string type into the boundaries of the cat. Okay. And kind of the emergent property, or what you expect from these models, given that it's a non-degenerate input, is that you have anions described by the input on the boundary. And in the bulk, it's just some trivial phase if you don't enforce a symmetry. It's kind of short-range entangled. And there's a subtlety here, which actually is not super important for my story, but it's very interesting, that when the boundary is kind of chiral, the bulk, you can argue the bulk can't be trivialized by a local unitary circuit. So we have to consider this more general notion of locality preserving unitary circuits to trivialize these bulks. And there's some nice work about this, I think, in these references. This ends up being related to non-trivial like quantum cellular automatas, and it's a whole nice story, but it's not super important for my purposes. I'm basically just going to allow these locality preserving unitaries in my trivialization procedure. So I'll call something short-range entangled if you can trivialize it with this. Yes, please.
Maybe you are going to mention this later. So for non-degenerate abelian TQ modular tensor category, I think you are saying that the Walker-Wang can be interpreted as a one-form symmetry SPT in bulk. And what about the case when it's a non-abelian modular tensor category? Is there still a SPT interpretation of the Walker-Wang?
Yeah, very interesting. I think that's one of my questions, like in the general case. And I know definitely other people have asked this. I don't want to take credit for asking this question, like Tyler, for example, is asking this question. But basically, like, what is the right notion of one-form symmetry for this general case? I mean, if you can kind of play the same story, and you imagine your symmetry is sort of generated by the anion fusion being satisfied. And then in some sense, it seems like these Walker-Wangs are always SPTs of this, but I don't know the right description of the symmetry. Maybe it's like one of these categorical symmetries.
Non-invertible defects, yeah.
Yeah.
Okay, thanks.
I think that's probably, some story like that probably is true, but I'm not going to get to that in this talk.
Okay, thanks.
Great. So let me see, I shouldn't skip past this. So in the bulk, right, what do we have? I said it's sort of short-range entangled without the symmetry protecting it. The symmetry exactly given by these vertex terms and producting them up. But if you, so the relevant operators you should sort of think about are the ones you get from the anions. And what happens if you kind of put some loop of these anions in the bulk, because you have this non-degeneracy condition, and I'm on every plaquette, I'm fusing in all the strings into the boundary, they won't, some strings from each plaquette that this string that I put into the bulk goes through will anti-commute with it, which means it'll pick up an energy penalty from every plaquette it passes through. So these kind of strings in the bulk are sort of confined. And you don't get any kind of deconfined topological excitations in the bulk. But when you play the same game on the boundary, you can kind of fuse one of these strings onto the boundary, and resolve it into a lattice. And if you do it from the outside, say there's some surface here, it doesn't have to pass through any plaquettes. So only at the endpoints where it breaks the kind of fusion rule, you have some excitations, is the idea. That's how you see that from this model, you get just the anion lines you plugged in as the boundary. And this is, again, using the non-degeneracy condition. Okay. The ground state of this thing is really similar to the toric code example. You just have this sum over closed anion diagrams, and then you have this phase factor, basically, which is the phase to create a given configuration from the vacuum. So again, yeah, you can kind of interpret the ground state as this history, well, it's some of it like different kind of histories, if you like, if you pick some direction to be time of these anion world lines doing things. Great. And then what is the one form symmetry? So it has this neat form here that you can sort of define some, I guess I've unfortunately changed basis from X to Z, but for my symmetry, I'm now going to call it acting in this kind of modified Z operator basis. And the way I define this modified Z operator is just putting a loop. So I have one of these for each anion type, and I just put a loop of this anion around this edge of my lattice, and then I resolve it in using the braiding rules of the anion theory. So I'm going to pick up this phase, basically, which will end up being a fusion character, I think, up to normalization. Yep, so this will be some non-trivial phase because of the non-degeneracy condition. So every anion commutes with some other, and doesn't commute with some other anion in this braiding. So this is the way the symmetry will act on site. And the group will be exactly the same group you plugged in to the Walker-Wang model. And so if I take the product of these guys over the edges in a dual, in a surface in the dual lattice, it'll be exactly equivalent to just in this picture language, putting these little loops of A around all these edges. But then if you kind of think about it, you have these loops of A on all these small loops around the surface, and you can just kind of product them up. And they just disappear because it's abelian. So that's one way of seeing why this is a symmetry. Alternatively, you could see that actually these guys, these Z's around a vertex, if you take a product of them around a vertex, are just given by some, they're just, they're dependent basically on the vertex term. So if the vertex terms are satisfied, the product of these Z's around, for the same A around the vertex also has to be satisfied. So that's, I guess, another way of seeing that this is a symmetry of the Hamiltonian, the Walker-Wang Hamiltonian. Okay, great. So yeah, this is just another way of seeing this picture of what the symmetry is doing. Basically, if you look at resolving sort of some operator at the top corner of this, you put a little loop of A into your lattice, and then as you kind of eat up the symmetry, you're just moving this loop over the surface, sorry, until it annihilates. So that's in some sense how the symmetry is acting within this ground state.
But so the difference with actual three-dimensional topological phases is loop excitation is still kind of a trivial excitation, is that right?
Yeah, if you ever, so actually that's exactly a good point. That's the next slide I'm going to show. If you do some restricted action of the symmetry, this making a domain wall, like making the loop excitation, this loop excitation is confined. So I didn't draw the energy penalty here, all the terms it anti-commutes with, but it anti-commutes with a whole bunch of terms.
So what do you mean by confined?
Yeah, maybe I shouldn't say confined. If you were thinking of this as a string operator for point particles, this would have an energy penalty going like the length. But
yeah, you want to think about it in a three-dimensional topological phase, you have a loop excitation.
Sorry. Yeah.
Its excitation does scale proportionally to the length. Mm-hmm. We don't call that a confined loop excitation. It's just a loop excitation, right?
No, you're right. You're right. I think how to see that this is not a non-trivial loop excitation. This is a good point. So when you create one of these domain walls, so if you act with this symmetry in some restricted region, you make a domain wall. On the ground state, it's equivalent to just plugging in this loop operator, right? And resolving it to the lattice. This is not in a non-trivial superselection sector because I can just act within the small neighborhood of this line and I can delete it. That's the way to see that it's not a non-trivial superselection sector loop excitation. Hopefully that answers the question. Yeah, so you can just make the domain wall of this symmetry directly acting within a small neighborhood of the domain wall by just plugging in this line into like the lattice and then fusing it into the lattice. And that should have the same action in the ground space as doing this restricted symmetry. So I guess the upshot is that the domain walls of this codimension 1 symmetry that I was calling Oneform are on the ground state are exactly given by these operators that basically just fuse this anion lines into the lattice. Okay. So yeah, maybe I should say one more word about that. So this basically is telling you already that because of the properties of these lines, the domain walls of this thing are described by exactly the abelian anion theory, basically, of these lines. So it is kind of, in a way, obvious when you just rethink about it, like, well, what are the domain walls? Just these abelian lines in 3D. And then what is the theory of abelian lines? In 3D, it's just some abelian braided fusion category. And in this case, I've put in this non-degeneracy condition.
So what happens if you take this Oneform operator, X on surfaces, but now do it on a non-trivial cycle, like you assume that you're on a torus and you do it on a non-trivial cycle. Is there anything non-trivial that happens there compared with a case where it's actually homotopic to nothing?
Yeah, so it doesn't do any interesting logical operators. But how to explain that?
Well, if there's no ground state degeneracy, then I guess you can't implement a logical operator.
Yeah, that's true. And then I guess that it's kind of a little bit, it's a bit non-obvious to see there's no ground state degeneracy with Walker-Wang, right? Because you can have like some loop configuration that goes all the way around the torus. But I think that one is not allowed in the ground state, because if you have a torus, you can pull some loop over a cycle of the torus that's generated by plaquette operators, and that will kind of kill or give an energy penalty to this loop that goes all the way around some cycle, which is why these operators don't act non-trivially. Or maybe another way of saying it is, if you have this non-trivial cycle manifold, then this is just going to be moving over the torus some like line of this anion line. But this anion line we know is in a trivial superselection sector. So probably you can in some sense, you can break up this whole non-trivial cycle into small pieces that each just act like a little loop of the anion, which is in a trivial superselection sector. So it kind of can't braid with anything, because its braiding would have to be trivial, because it's kind of not in a non-trivial superselection sector. Yeah, hopefully that makes sense. Okay, right. So in the bulk, these anion lines sort of, not too surprisingly, described by the thing we put in, which is just some abelian category. And then this is kind of so you can, the symmetry is just determined by this A group, but if you change the quadratic form, right, you get different theories basically, and these are the different SPTs. And this will come in with the boundary. So you always have this sort of similar kind of pretty boring action of the codimension 1 surfaces, but then the way they act on the boundary is determined by the model. And this puts some constraints on how these domain walls act when you push them to the boundary. And the basic idea is just that these lines that are domain walls in the bulk, when you push them to the boundary, have to retain the same braidings. So there's some braiding information, which is some topological information or processes you can define for the domain walls. And if everything's symmetric and you have a symmetric boundary, there's no way for these to change basically as you push these domain walls onto the boundary. And on the boundary, they exactly just become these string operators. And so that probably can rephrase this in terms of this inflow. So if you have some boundary theory, it's going to have some anomalous symmetry action. I use it in quotes because I'm not sure if this is the right way to use anomalous, but maybe it is. And because of the way the domain walls behave, these string operators on the boundary, in this case, will have some non-degenerate braiding between them, which tells you in particular from like a torus, there has to be degeneracy. And so if you want to preserve the symmetry, you can't have like a unique gapped ground state that is symmetric. You have to at least have like this topological order. And a topological order consistent with the symmetry in this modular case is pretty obvious. It's just like take the theory described by the data you put in, and that will match the domain walls coming from the bulk. Okay, so there's just this more general version of the same picture I showed you earlier. If you have a symmetry for this group element A in the bulk, it's going to, and you're acting on the ground state, it's going to have an equivalent action of just these string operators for the A anyons on the boundary, which are like just the domain walls of the symmetry pushed to the boundary. And in Walker-Wang, it's all very explicit. Like you actually have these lines and you have some way of turning them into operators on your lattice model by just fusing them into the lattice. Okay. So then now that we know this, basically we can just run the same argument from the example. If you measure out some region in the symmetry basis, which is possible because these are all just sort of diagonal symmetries in the string basis, you'll find this world line history of the anion theory you put in, which you can use to kind of correct the state you get afterwards if you want it to be exactly doing the identity gate or making just the usual sort of Bell pair maximally entangled state. And because I measured this sort of a slab out, the symmetry action there, if I had like some symmetry action that was equivalent to this pair of anions, it's just going to become like some number. I mean, if it was Z2, it would be a plus or minus 1, but more generally, it could be like a phase from the measurement result. And so then I get that these two string operators above and below, where I measured this out, that were given by like domain walls before, but now will become surface operators, are going to be like perfectly correlated. And this will show you that, you know, in the ground space of these sort of topological boundaries, you get you're preparing perfectly entangled spins within the topological ground space. So yeah, this is sort of just generalizing the exact same thing we did for the Torah code to this general case and using the symmetry properties and their domain walls to argue for the fact that you get this localizable entanglement when you measure out a region in the symmetry basis. So hopefully that makes sense in this general setting. Great. And then I want to talk about the existence of this this phase to finite temperature. So this is actually similar things have been thought about, I think, before, and also so if you kind of maintain the symmetry, a similar mapping has been used to argue you have like a phase transition at 0 temperature if you add in symmetric operators, but I'm going to talk about sticking to the same Hamiltonian but going to finite temperature. So the way this has been defined to talk about this symmetry-protected topological phase transition at finite temperature is you kind of really enforce the symmetry. So I basically crank up the vertex terms to have infinite strength in this model, and then consider going to some finite temperature with this Hamiltonian, but with the vertex terms really enforced. This thing just becomes like a projector onto the space of string fusion rules being satisfied. And so I have this, this partition function is going to be the trace of these plaquette terms against this projector. And then at high level, basically, if you're within the subspace of this PV, these plaquette terms form exactly the same like plaquette algebra as an Ising gauge theory with just A spins. And so this up to just basically you getting the trace of this projector instead of the trace of identity. The terms that contribute to this will just be exactly the same as that. So the partition function up to just some constant factor is exactly the same. And more importantly, the sort of generalized order parameters you want to put in are just products of these plaquettes. So in like the Ising gauge theory, this will just be like a loop at the boundary of the product of the plaquettes. In the Walker-Wang model, it will be more like I guess I would call like a disorder operator. I don't know if that's really the right word to use, but it's like going to have like a manifold with some boundary operator, some open kind of surface with a boundary string operator attached to it. That's the order parameter you want to use. And this, again, because of the algebras matching, will end up to this constant factor coming from the trace of PV being just the same. So when you see the phase transition in one order parameter, you'll see it exactly in the other one. And it's sort of if and only if.
So sorry, well, once you impose this constraint, so right now you're sort of looking at a constrained Hilbert space. Mm-hmm. Is it not true that the one-form symmetry actually acts trivially in that Hilbert space now?
Yeah, I think that would be the right way of saying it. I mean, definitely if I don't think of having a boundary, which is kind of the way I've written it, you're just enforcing it like strictly.
So somehow it's weird to think about a one-form SPT for a one-form symmetry that isn't really acting non-trivially.
Yeah, I think it's somehow it's only, you only see that it's interesting if you introduce a boundary. And then I think actually I'm going to show this in the next slide. Yeah, exactly to your point there. Okay, is there a question? Go ahead, Hank.
Yeah, I'm just wondering, because to define the Walker-Wang model, you have to refine the layers. So if you have like more than a 3 valence vertex, you have to sort of split them. So I'm just wondering, if you insert the loops into one of those split vertices and then you try to unrefine those things, what happens to the loop?
Yeah, a good question. I kind of skipped over this because I think the neatest way to write all these models is to not resolve the vertex.
Oh, okay.
So you don't actually have to resolve it. And this has already been like covered by some old papers by Bernal and Simon and von Kaiserlink. I think that kind of explained that for abelian anyons, you could kind of recollapse the vertex because it's kind of redundant information inside these resolved vertices. But if you did resolve the vertex, like I showed, then this would still, these would still be the generators of the one form, basically. Like you just take some anyon loop and go around one of these resolved vertices. And so in some sense, it's slightly different lattice model, but the overall properties should be basically the same, whichever way you do it.
Okay.
Okay, so yeah, coming back to this point of when you enforce the symmetry, what's going on, it is pretty restrictive and it almost looks like nothing interesting can happen, because if you kind of try and make, so imagine we have a boundary now and we're really enforcing this symmetry, and say we're within this finite temperature phase, but before the phase transition. So we still have this property that the domain walls are described by these anyon lines, right? On the surface of this thing, you can't have isolated anyons appearing just on their own, because this breaks the one form symmetry if I'm really like enforcing it with this infinite strength. So these things don't happen. So you can try and push these into the bulk, but you then pick up some energy penalty and they still break the one form symmetry in the bulk if I have these endpoints. So the only way to define some operator that's kind of acting on the surface with a string operator, but doesn't break the symmetry, is by pairing these up. And so if everything's kind of flat, this is going to lead to an energy penalty of making a string operator on the surface that scales with its length, basically, if it's going in a straight line, at least. And this is kind of the property you want for, or at least a sort of a sufficient condition in some sense, unless, well, it's also not a sufficient. So I don't want to get too much into this idea of self-correction, but the idea with self-correction is that an energy barrier for the errors that you want to suppress happening is very important, because if you have a large energy barrier, then it's going to put like kind of an exponential suppression in the energy barrier on these processes happening in finite temperature. And this gives you a really good energy barrier. It's kind of a subtlety that you can come up with crazy models that kind of get around even having such a good energy barrier, but in this case, that's not happening. And there's some previous papers looking at this behavior for toric code and 3 fermion example. And I think something similar is going to be true for all of these Walker-Wang models. Basically, that you'll get this linear energy barrier when you're in this like symmetry enforced finite temperature phase. And this should be enough to ensure that you really get self-correction on the boundary, which is to say that if you kind of take this model and let it sit there with the symmetry enforced, and then so these anyon hoppings can kind of happen on the boundary, but only up to being tied to these loop operators going through the bulk, that you can come back like some sort of time later that scales with the size of the surface. And you'll find that with very high probability, none of these anyons have gone very far, because they have to be tied to these very energetic loops in the bulk. So the process that you want to suppress really is some anyon going around the whole surface in one go, which would have very low energy. But if you have so this other assumption that the noise is kind of local, or that these hopping steps happen in local pieces, then this should be suppressed by some very big energy barrier, which is going like the linear extent of the surface that has to be overcome to like hop in small hops around the whole surface, basically.
So just to be clear, which phase is this? Is this in the high temperature or the low temperature? phase.
Oh, sorry, this is a low temperature phase. So
in the high temperature phase, what happens to the one-form symmetry?
I think it's still, well, the phase I'm talking about is it's still enforced. If you kind of break it at all, everything just becomes trivial once you go above 0 temperature. But if you kind of strictly enforce it, like I said, in the high temperature phase, I think I'm not totally sure, but it should become trivial, more or less. I think the domain walls become like confined in the sense of scaling like the volume enclosed by the
in the systems I know, if the one-form symmetry is exact and there is a phase transition, then it can be thought of as being unbroken in the low temperature phase, but then it is spontaneously broken in the high temperature phase. Is this the case here?
I think that would be the case. The only thing I'm slightly confused about to make the claim exactly is that this order parameter is kind of a disorder parameter for this Walker-Wang model. For the Ising-Gauge theory, then I would agree with you definitely. But in this case, the order parameter has this like surface operator as well as the line around the boundary.
Well, how you represent the symmetry shouldn't affect the answer, whether the symmetry is spontaneously broken or not.
Yeah, the symmetry is the same. That's true. But this order parameter for the symmetry will be different in my Walker-Wang phase transition versus the lattice gauge theory one.
Maybe I should ask it differently. Is the one-form symmetry an exact symmetry of your Hamiltonian, including at high energies, or is it only a symmetry of the low energy physics?
When it's enforced like this, then I think it would be exact. And yeah.
Okay,
it's exact, but it's also nothing, right? That's what I was saying before. It's a confusing thing.
What did you say?
It's exact, but it's actually acts trivially. So it's not a non-trivial exact symmetry, or at least it doesn't seem like it is.
At high energies or low energies?
I mean, so if you impose this constraint condition, then you assume the constraint is opposed, in any temperature, which is what it's saying if you make the coefficient infinite. Then Dominic, you were saying, it's an exact symmetry if you impose the constraint, but it's also a trivial symmetry in that case.
Yeah, I guess I don't know exactly how to square that it's trivial, but if you look at the way it acts on the boundary, it's a pair of line operators, and one of them alone could be kind of non-trivial.
Yeah, I feel like somehow we're not thinking about trivial in the right way. Like there's some sense in which it's non-trivial, even though looks like it's the identity operator.
Can we clarify the starting point? You have a Hamiltonian, and let's put it without boundaries, periodic boundary conditions.
Mm-hmm.
So there's no boundary, and there is a charge. Does it commute with the Hamiltonian? And does it act non-trivially on anything in the Hilbert space?
I don't think the charge commutes with the Hamiltonian in this case.
And it acts non-trivially on the Hilbert space. So there's states with different charges.
No, there would only be one state in this Walker-Wang.
But then it would mean that there's no such operator. The operator is the identity.
Yeah, I think that's what Dominic
said. But then there's no symmetry. So you can't have it both ways.
Mm-hmm.
I believe this is related to the confusion that Dominic has. Is that right, Dominic?
Yeah, I'm wondering if there's some notion of non-trivial one-form symmetry that still exists when the operator is trivial, but okay, I don't know how that would work.
There's an invariant way to answer that. Is there a non-trivial operator that commutes with the Hamiltonian and acts non-trivially on the Hilbert space? And has some non-trivial commutation relations with operators, etc.
Oh,
if the answer is yes, then there is a symmetry. If the answer is no, then there is no such symmetry.
Yes, that's a very clear way of saying it. I think if you have the torus, then the answer is no. But if you have an open surface with this symmetric surface termination, then you can find something that anti-commutes with the symmetry.
Also, Dominic, in this Tari code and 3-Fermi examples, right? You don't have to impose any constraint. I mean, the symmetry is exact for the Hamiltonian.
Mm-hmm.
So in that case, it's the one-form symmetry is non-trivial, not identity.
Mm-hmm. Yeah, I guess in this case where you enforce it, though, it seems a bit different.
When you enforce it, that's different.
Mm-hmm. But yeah, when you enforce it and you don't have a boundary, it does seem to be acting trivially. Maybe
Ryan, Ryan, are you there? Do you agree with Nadi's definition? I feel like there may be something.
I was going to say I agree with Meng. It has to do with whether you're imposing these constraints, like that the fusion rules are satisfied at the vertices, whether you're imposing those as terms in the Hamiltonian, or whether you project those out of the Hilbert space entirely. If you project out any state violating the constraint, then I believe you've projected out states that are charged under these one-form symmetries. So they're kind of hidden in the constraints. And if you work with a local Hilbert space, like you don't impose any constraint, you make sure everything is done energetically, then there'll be some gap. Above the gap, you'll have charged operators, charged states, and below the gap, it'll look like the identity, but of course it's not really.
Yeah, I totally agree with that.
Big related comment. So in the continuum, right, the way we think about SPT is an invertible field theory. And invertible field theory has a unique ground state on any closed spatial manifolds, and the symmetry by construction will act trivially on that unique ground state. And we can only see the non-triviality when we put the SPT on a manifold with boundary.
Yeah, but somehow there's some sense in which maybe not on the ground state, but on the data of the invertible field theory, the symmetry has to act in a non-trivial way in order for it to do anything non-trivial on the boundary.
But in that case, either you do it on boundary or introduce defects, right?
Yeah, or you couple to a background gauge field for the one-form symmetry.
But otherwise, you don't really see anything.
Yes.
But the statement is maybe it's possible to have a non-trivial response to a background gauge field for one-form symmetry, even if the one-form symmetry acts trivially on the ground state subspace. Is that possible?
Mm-hmm. I think that's what it would be saying by the fact that although it's acting trivially, it's still kind of, you can make these configurations where you apply a restricted symmetry action and a domain wall, and that's not acting trivially. You do see the domain wall, right? And this domain wall you'd see with coupling to background gauge fields.
Right. Yeah, so it's not really a trivial one-form symmetry, even though it's X as an identity operator. So that's kind of contrary to what Nati was trying to say as the definition, it seems like.
I think you can draw an example with very familiar SPTs, like say you studied the cluster SPT in one dimension. You can project out all of those ZXZ operators, right? You can just take the projector that ZXZ equals 1. It's very similar to imposing like a Gauss law. And then there's only a one-dimensional Hilbert space. All operators are the identity. But nonetheless, if you take the symmetry operator and you try to truncate it, then at the boundary, you'll have to have a violation of the constraint. So yeah. that's the what's it called? The evidence of the SPT, that you can't stay in the constrained space if you want.
I agree with Ryan. I think the issue has nothing to do with the fact that the symmetry is one form. It's already there for the 0-point symmetry.
So in this case of the 1D example, that's good. We could make a configuration that satisfied the constraint, right? But we had a restricted symmetry action and then do something on the domain walls to put it back into the constrained space. So it's not taking you out. And if we isolated one of those domain walls, like push the other one to infinity, you'd probably be able to see the properties of the SPT phase from that. I think something similar is happening in this example.
I mean, I guess you can actually write a Hamiltonian that has all these symmetries, full symmetries, right? You just write AV and BP, BP together with a projector, then the symmetry will be there. And then the symmetries are only acting on the charge states, which are highly excited. Well, not highly excited, like excited states. And it's, and as Shuhan just said, it's not really different from the other one-form symmetry or even SPT example.
Mm-hmm. Okay. Yeah, hopefully this slide made sense. I think this discussion really helped me think about it a bit better. But I'll move on, I guess, if anyone else doesn't want to make a comment. Okay. So I've told you about this, everything I want to tell you about this, basically reinterpreting modular Walker-Wang models for abelian modular categories as one-form SPTs and seeing generalizations of these various properties people have derived before for particular examples in this setting. And now I want to tell you a bit about this question from earlier. If we consider the more general story and we drop this non-degeneracy condition, and how to see that in Walker-Wang models, basically. So if we kind of take a more general view that we just have some SPT phase with this codimension 1 symmetry given by some abelian group, and we want this SPT phase to have a unique ground state and be trivial, up to QCAs when I remove the symmetry protection. And then I can ask about classifying these things, and I think there's some probably pretty old idea, I don't know exactly the right reference, but to classify SPTs via the domain walls. I think you can extract everything you want by the topological theory of the domain walls. So in this case, this, like I said before, is just going to be this theory of like abelian lines in 3D. So it's going to be an abelian braided fusion category. And I think if you put in unitarity assumption in the symmetry, it's like a unitary abelian braided fusion category. But there's nothing telling you it has to be non-degenerate. That's the difference between this and what I was talking about earlier. Okay. And so the thing describing these domain walls is just, again, this data of the abelian unitary braided fusion category, A and Q, but Q can be degenerate. And so again, I have these domain walls given by A, and I can push them to the boundary and get some excitations, and then there should be the sort of braiding statistics of these boundary excitations has to match with the data of these domain walls in the bulk. And this AQ data tells me everything about these braiding statistics. The difference comes in now because they don't have to be non-degenerate. You might have some degenerate thing living on the boundary.
What if they are all bosons?
Yeah, good question. So what does this boundary theory have to be? What is the constraint coming from the bulk? Imagine they're all bosons. There's no constraint, right? This is like the trivial SPT. If you write the Hamiltonian, it'll just be like X on every site. So the constraint it puts on the boundary, the way I was thinking of saying it is basically it just has to be some modular extension of this, what you get by taking this braided fusion category and basically quotienting out these transparent bosons. By transparent, I mean they have trivial braiding with everything else, and they're bosons, so they have trivial statistics with themselves too. So once you quotient those guys out, the thing left over is what has some kind of anomaly inflow to the boundary. And then it might be pre-modular still though, up to a fermion. And so I think the boundary basically, to be consistent with this, just has to be some modular extension. And the motivation for it being modular on the boundary is like, if you're putting some assumption of like remote detectability of the charge sectors that are stuck on the boundary. Yep. So if it was fully bosonic, like everything was transparent boson, you would quotient it out and you would say like the boundary is just nothing, which is a modular extension of nothing.
Okay, thank you.
This is for the symmetric boundaries too, sorry. I should always say that when I'm talking about the boundary, I mean the symmetry preserving boundary. Okay, so what happens if you have some degenerate thing that isn't just fully bosonic? Oh, sorry. Right, we talked about the properties of these SPTs, but what happens if you try and realize these in Walker-Wang models similar to what I was doing before? Well, the thing that the naive guess, I guess, would be, well, you can just plug this data into Walker-Wang because Walker-Wang takes a braided fusion category as input. It doesn't have to be non-degenerate. But if I plug this non-degenerate thing into Walker-Wang, what I'll get is that the transparent bosons and fermions, basically, in this input data, can move around the bulk. They can move from the surface into the bulk and just wander around like 3D particles. Things that are not transparent are still going to be confined to the surface. But I'm going to get this more complicated theory with some stuff that can go into the bulk and can talk to these things on the boundary, like fuse with them. And then there's these other sectors that are just confined to the boundary. And the things that can move into the bulk have trivial braiding with themselves and everything else. So they have to be bosons or fermions, which is consistent with them being some point particles in the bulk. Okay. And then having these point particles in the bulk defines some dual topological sectors that are loop-like, given by the eigenvalues of braiding with these particles. So if I have some string operator of the transparent particle, it is like not confined now. It's going to give you a good string operator in the bulk that commutes with everything if I resolve it into the lattice. And eigenvalues under these small loops of this will define some flux strings. So you'll have in the bulk basically some abelian gauge theory basically that could also have fermions as determined by this quadratic form, the degenerate part of this quadratic form.
What is the theory in the bulk here? Is it the walk? What is it? Okay. What is the theory in the bulk?
Yeah, sorry, I jumped. I'm not talking about SPTs anymore. I'm talking about if we want to try and use Walker-Wang to realize these SPTs. and I just plug in this degenerate quadratic form and
I understand, but is there a concrete theory in the bulk that leads to all that?
Oh yeah, so the like emergent theory in the bulk would be just the take the degenerate part of this.
No, not degenerate. It's a microscopic theory in the bulk that at low energies gives you this SPT.
Oh, the SPT from the previous slide. That's exactly what I want to get to. So this thing I'm showing you here is not an SPT in the bulk because it has these topological sectors basically, and some of the
it doesn't matter for my question. The reason I ask is that there are 3+1 dimensional theories that lead exactly to this setup, which is either SPT at low energies or some ZN gauge theory, or some, in general, some topological field theory in the bulk. And there's an anomaly, and the anomaly is associated with a non-trivial TQFT on domain walls or boundaries. So I'm curious whether what you have is the same or not.
Oh yeah, I think maybe you're talking about this paper you're on, which I think some of the things we're going to say now are exactly just some lattice version of results in your paper about duality between having a certain anomaly on this symmetry in the bulk, and if you do the gauging duality, you either get an SPT or a topologically non-trivial phase.
Okay, maybe we should continue and then we can compare.
Yeah, maybe it'll make more sense in a minute. So the thing I'm talking about on this slide is exactly just taking Walker-Wang and plugging in this pre-modular abelian category. And so you get some topological sectors in the bulk if there's a degenerate part. And you still have this non-degenerate stuff that's confined to the boundary. Okay. And oh yeah, so you still additionally have these lines that are kind of confined will have this energy penalty in the bulk. And I think it's sort of, it can go two ways. Like they can also be kind of tied to these loop excitations, or they might be trivially created, but it depends on the exact model. So the bulk of this thing is definitely not an SPT of the, or even an SET necessarily of this A group you've put in as a symmetry. So how do we turn this into an SPT under this A sort of codimension one group that has the right domain walls? So I guess one idea is you could try and take Walker-Wang of this degenerate thing into a modular extension. I think that might work, but that's not the direction I'm going to go in. Instead, I'm going to do gauging duality on this symmetry group. So I have in this Walker-Wang this.
I apologize that I sound like a broken record. Maybe some of you are too young to know what that means. But what is gauging duality? It's either gauging or duality.
Mm-hmm. Yeah, I think I'm going to do gauging, and then I'm going to use it to come up with a model that I would call a dual model.
Well, so you're doing gauging, which might or might not be dual.
Mm-hmm.
Okay.
Yep, I'll say how I do it in a second. Okay, yeah, so I start with this Walker-Wang model, and I have this Oneform symmetry that's basically these, I have these qubits with these EM groups, and there's a natural kind of Z operator on these, which is generalizing the thing from earlier. It doesn't have this nice picture that it's just equivalent to inserting some loop of anion type because it's degenerate now. So some of them might have that, some might not. That nice picture is not there for all of these operators, but I still have an A group basically coming from the qubits on, so there's A string types on this edge, and there's a natural kind of grading operator on them, which assigns some phase depending on the string type. And these will commute with the Hamiltonian. They're generated by these vertex terms again, and they'll give you some action of this kind of codimension 1 asymmetry. And I want to couple this local action of this symmetry on a single edge to gauge spins, A gauge spins living on the plaquettes, to turn this into a local symmetry. And what it does to the Hamiltonian is it doesn't modify this vertex term at all. It modifies this plaquette term, which I'll show you in a second, and introduces some new terms. This edge term, which will be like kind of like enforcing the Gauss's law, and I'm just doing this energetically for now. And then there'll be some extra term, which is like generators of a dual symmetry, which, yeah. So I'll tell you what that is in a second. So the vertex term is the same. this plaquette term, I now have an extra degree of freedom on the face labeled by some A variable. So this subscript F is for the face. And what this BPS operator does now is, so if S has this grading label G, it fuses this string into the boundary as before, but it also hops, it left multiplies or right multiplies. It doesn't matter because they're abelian this group element on the face. So like the only difference is now when I insert this string with this BPS operator, I left multiply the face variable. And the reason, okay, so this is just showing, again, to actually define this thing, you kind of clear the plaquette, and then you just resolve the boundary string in, you get the same matrix as before, along with this hopping of the plaquette variable. The reason to attach this plaquette action to this guy is to make it commute with the Gauss's law term. This is kind of tying the local symmetry action or the grading label on an edge under the symmetry to these gauge degrees of freedom. So if you have 4 of these gauge plaquettes coming into an edge, they don't have to be flat. They can have like a non-trivial group element product around this edge. And this term just ties that group element to the label of this string on the edge. Or if you like, if I read this in terms of operators, I could basically have some kind of generalized Z operator in all the plaquettes and a generalized Z operator on the edge, which is measuring the label there and the labels on all the edges. I mean, the plaquettes, sorry. And then this cube term is just a dual symmetry generator, basically. So I'm going to get actually a dual codimension 1 symmetry, which is given by just like left multiplying these group elements on the plaquettes at the surface of a cube. So I'll have this on every cube, and if I multiply them up, I'll get some action on like a surface of a big cube or different kind of discretized codimension 1 shapes. And this is the symmetry I want to think about. So this is going to again be the same group A by construction. And so these will generate an A codimension 1 symmetry, which is the one I want to focus on now in this new model. Okay. So kind of by construction, in this dual model, I've made it so that the domain wall of the symmetry acts exactly like fusing in an anion line that is described by this input data A and Q, where Q could be degenerate. And the reason for this is because of these plaquette terms. So the plaquette term basically tells me if I'm within the ground space, that when I act on a plaquette with this symmetry, it creates some domain wall, and the domain wall can exactly be kind of canceled out by fusing in this loop of string type SG. So this is sort of telling me that in this gauged model, if I focus on this symmetry generated by this, by construction, it's kind of domain walls are exactly described by the data I want. So you could kind of be more careful and look at different processes, but hopefully this is enough to convince you that this is kind of achieve the goal I want. And this non-degenerate string types described by AQ are now being realized as the domain walls of this codimension 1 symmetry on these cubes. Okay. And then I wanted to make contact with some previous work, because like I said earlier, there are existing works on classification of one-form SPTs, and they look a bit different to this model, so you might wonder why. And to bring this into the right form, there's some symmetric local unitary circuit that basically just decouples the edges. So it sets them into this like +1 state under these terms, and they just drop out. It does some kind of complicated thing, pushing the terms that were acting on the edge from this BP onto the surrounding plaquettes. And I'm not going to show exactly what that is, but if you go to the dual lattice, just to make contact with exactly how these other models were written, you end up getting that what was this BPS term in this dual formulation is just going to be like a single site left multiplication, and then some kind of phase factors, basically, that are coming from what were these kind of these like sticking up braiding terms you got in the Walker-Wang. And these models, at least for some subclass, match exactly with these, I think, with these earlier models found for these one-form SPTs. Okay. Let me see. Okay, maybe before I just go on to the last little bit, yeah, was there any, do you want to ask any questions about the gauging of this Walker-Wang model that I did? So I think this model I was kind of calling the dual model, but the previous model I would just call the gauged Walker-Wang model. Okay, cool. So yeah, this is the kind of the way to realize all these degenerate SPTs.
Can I ask a question?
Yeah, please.
So to recap, so you had like some pre-modular Walker-Wang model, right?
Mm-hmm.
So we can have the theory with anyons at the boundary, and when you're doing this gauging, are you at the boundary condensing the center?
Oh yeah, that's perfect. I'll go into the next slide. So I think this ties into Natty's paper. When we first were thinking about this, we were kind of excited because we were like, you can do this gauging, and then on the boundary, it's like condensing anyons, right? Which could be in the center, but they could also be, you could apply this to the usual Walker-Wang too. Because I'm just gauging like the whole group, the whole codimension one group. So this could like be condensing anyons beyond bosons or fermions. And it turns out that's actually not so interesting. But in particular, it does, it can condense the bosons and fermions. And I'll describe that on these slides. Actually, I think it's my last thing before the conclusion.
So just to check, the reason why you're doing your gauging is just that you want to prove that you have a one-form SPT, or
yeah, I wanted to find one-form realizations of all these SPTs, and before we only had the non-degenerate ones. But yeah.
So actually, you still have a global one-form symmetry in these models. Is that
yeah,
right?
So the one form under which it is an SPT is this one, the one generated by this term.
Okay, cool.
Okay, so
still a little baffled by why you have this elaborate construction, because after all, the symmetry is only a product, is a product of ZNs. And there aren't that many anomalies that it can have, just from the general classification.
Mm-hmm.
And so all the information is captured in a small set of integers. And in simple cases, it's just n for one ZN and some integer that labels the anomaly in that ZN. And then it's really straightforward to write the SPT phase and to find what the anomaly is for the theory on the boundary. So why do we need this whole elaborate construction of Walker-Wang and so forth? And then if you want to gauge anything, it's also straightforward to just gauge any subgroup of the one-form symmetry.
But I think the input is the same, right? The input is a premodular category. You specify the group A, and then the Q in his notation is exactly the anomalies of
which was also denoted as Q in the original papers.
Yeah. So at least the input.
So this is the data, and you don't need anything else.
But Natty. Yeah. So I think the point is that if you just naively, at least in this Walker-Wang model, if you naively input the premodular A and Q, you don't get SPT. You get a non-invertible theory, right? And then Dominic did this.
No, but the same thing is true in the way I think about it. There's a ZN gauge theory in the bulk, which you write in whatever way you want, and with the one form ZN gauge theory, and then you can add a BB type term that captures the modification, and which is labeled by some integer, and that's all the data. And
yeah, the data is the same. I mean, the BB term, actually, if you write it on a lattice, is exactly Walker-Wang.
Yeah, but this is straightforward to write in the continuum, and then the gauging, everything can be done with far fewer steps, right? In fewer terms. Mm-hmm. There's huge literature on these theories and gauging and not gauging and what's on the boundary and so forth. So I do not see why. I thought that we need the Walker-Wang construction if we want to find new examples, or we would like to hit the system and do all sorts of things. But you don't do that. You just kind of discuss what phase we have, what global symmetry we have, and then what subgroup of it we gauge.
I mean, I totally agree that these models are just doing some, okay, slightly different or maybe the same lattice version of this paper that I think you and others have about gauging the one-form symmetry. I think that the reason for using Walker-Wang was kind of trying to make contact with some using these states for measurement-based quantum
Just to get the
computation.
reference straight, all co-authors are present here.
Mm-hmm. Yeah, I think, sorry, I definitely have this one somewhere.
I don't care about the reference, but I just want to see the physics. What is added here beyond the by far simplest description, which already exists?
I think it's sort of just fitting this into, if you want to use Walker-Wang to represent the one-form SPTs, you miss some if you just use Walker-Wang, right? And this is how to make contact with the previous results. Basically, you just gauge it to, but I wouldn't say it's not a very good way of realizing the pre-modular ones, if you like. For the modular ones, I think it's a nice picture. For the pre-modular ones, not so much.
I see.
Mm-hmm. Yes, and it is kind of like, I don't know, just a side comment, because also I don't think the pre-modular ones are particularly useful for measurement-based quantum computing either. So maybe it's just sort of covering a comment of, well, why does this not cover everything if you use Walker-Wang models? Okay, you just do this extra procedure and it matches what we know. Okay, so I think the final thing I just want to say is about what this gauging procedure does on these SPTs. So this will kind of be going in the reverse direction of the previous thing, if you like. And for the modular SPTs, it also does something, but it's not so interesting. So in this, I guess the way I think about what the gauging does at a sort of higher level is that it ends up condensing the domain walls of the symmetry and promotes these twist defects you get by cutting open a domain wall into deconfined like gauge fluxes. And it promotes these irreps under the symmetry domain wall action to topological charges. So these twist defects of this codimension 1 symmetry will be point-like because the domain wall is 1D and then the twist is 0D, while these irreps under the domain walls will be loop-like because the domain wall is like a loop and it's acting by sort of collapsing onto another loop that's going through it. So for the non-degenerate case, these domain walls kind of have a self-duality. And from the point of view of the anion calculus, it's pretty clear from this non-degeneracy, because basically because of this non-degeneracy condition, the irreps of this algebra basically acting around a loop are just projectors onto the different string types. So I just wrote the action here, but if you form irreps of this, it's just projectors onto different string types. So like the dual lines to the lines you gauge when it's non-degenerate are just the same, basically, or a dual version of the same thing. The topological data is the same. And so, sorry, let me just say one more comment. So on the boundary, what this ends up meaning basically is if you gauge this non-degenerate thing, the anions do kind of condense in a sense, which is already covered in this paper, but this is just seeing it on this lattice model setting. They condense, and because they braid non-trivially with themselves, they kind of confine themselves out or condense themselves out. But then with these charges, they end up popping another copy of themselves back into existence. So in the end, it ends up sort of doing nothing on the boundary, because we also have this result that like, even if there was a bigger category of stuff happening on the boundary, if you have a non-degenerate subcategory, it sort of factors out. You can write it as the boundary is like a layer of this stacked with a layer of something else. And then when you gauge this symmetry in this layer, that's like the non-degenerate symmetry, it's just going to kind of kill the anions in this layer, but then create a dual copy of the same layer. So in the end, not doing anything really interesting, just making a dual version of the same SPT. And when you have these this degenerate case, let me just talk about the simplest case of when everything's transparent. This is like a pretty conventional case of just having like a trivial phase under this codimension 1 symmetry. And when you gauge it, the twists are just some abelian points. They become like point particles, and they're either fermionic or bosonic, determined by this Q. And then the fluxes under this domain wall action are just going to give you your topological loops. So you get your transparent particles and loops from this. And then you can have this like a more complicated mix of the two things, which just ends up producing this kind of bulk theory that's given by these pre-modular Walker-Wangs, which I talked about previously. Okay, yeah, so in some sense, this gives you some different way of just dealing with anion condensation beyond boson condensation on the surface, which could be nice. But it sort of turns out that if you kind of think of, if you have like a general case, a degenerate thing, if you gauge the transparent part first, this is just corresponding to boson and fermion condensation on the surface. And it does it by letting them wander into the bulk. And then once you've done that, you have a non-degenerate thing left. And if you gauge that, then it's kind of just doing some self-duality on the boundary. So it's not really doing anything beyond, anything really super interesting beyond boson and fermion condensation. Okay. And then, yeah, that's brings me to the end. I think there's like a lot of interesting things to ask, particularly on the MBQC side, which I think the most interesting thing is about, I only talked about really doing the identity gate, which is like the first thing you usually think about. But we obviously want to do non-trivial computations. And in this toric code example, people know how to kind of do this group of certain Clifford gates, well, all the Clifford gates, which you use some ideas coming from 2D toric code, twist defect encodings or hole encodings. And this should correspond in this phase story to some kind of two-group SPT where you have a global symmetry acting on the Walker-Wang model, which we've kind of looked at recently via some locality preserving unitary, or via like a generalized Walker-Wang model. You can make the action of these symmetries a bit more easy, the global symmetry. You can make it on site. There's like this recent paper by Bullmash actually that has a nice version of this that also works for anomalous symmetries. So in principle, we could, if we understood these phases well enough, we could use them to do some kind of MBQC with defects of even anomalous symmetries by sort of plugging them, the defects of these things into the Walker-Wang model and doing our measurement procedure. And we thought about a very simple version of this for the 3 fermion model recently. But yeah, the phases side of this story could be very interesting. And I should mention there's a bunch of papers already looking at some interesting examples from quite a few years back now by some subset of these authors. And then I think maybe another thing that could be interesting, although maybe it's also kind of already solved, would be thinking about the pre-modular, the version of this Oneform SPT story where you have a fermionic system. And there's been some recent work on this for a certain subclass of fermionic, well, actually 2-group SPTs. But maybe adding the Oneform could be interesting. And then you could sort of in the Walker-Wang model consider the shadow model where you have a fermionic toric code in the bulk enriched by some Oneform symmetry by using pre-modular Walker-Wangs. And then you would want to construct the fermionic model, condense this, immersion fermion in the bulk. And then I think finally, yeah, maybe a really interesting question is about the right notion of generalizing this Oneform symmetry or codimension 1 symmetry that would apply to like all of the Walker-Wang models, particularly the modular ones that could be non-abelian, for example, and how this might protect some potentially universal topological MBQC or some other model for computation within the ground states of these models. Okay, so that's all I have to say. Thanks for listening.
Thanks a lot, Dominic. So we already had a nice discussion and we went over. Thanks for everyone who stayed for the extra time. We can stick around and discuss, or if anyone has any questions.
Yeah, thanks all for the questions. Actually, this has really helped me with some understanding.
Actually, I wanted to bring up a question since Nati is here, and we already touched on this idea that like the Walker-Wang model, as an SPT, it has very simple data if you're just looking at the action of this center as a one-form symmetry. But in practice, it's quite amazing what happens where you get this chiral non-abelian order on the boundary, if you choose like a good Walker-Wang model. I never knew or still haven't managed to understand like what the relationship is to the framing anomaly, which is the usual thing people cite when we talk about why you can't have a 2D Hamiltonian that gives rise to a chiral model, and yet we can write this Walker-Wang model. Maybe it has to do with this some idea of like a generalized one-form symmetry, but I also think it has to do with the framing anomaly, and I'm not sure how they're related.
Would you be interested in this already just for an abelian chiral model?
Yeah, something like U1 level K would already be.
What's really the question? I fail to see. Is there a concrete question, or is it something that you would like to see in more detail?
Okay, so there are two questions, I suppose. Well, one question and then a follow-up depending on the answer to that one, which is, is it true that you can't write a 2D Hamiltonian that gives rise to, say, U1 level K Chern-Simons theory with nothing else, right? No gravitational part that makes it non-chiral. So we think that that's the case. We think that there is no 2D Hamiltonian that does
There's
that.
no commuting projector Hamiltonian, you mean? If you don't impose that requirement, you can.
Yeah, no.
Commuting projector and finite degrees of freedom locally, right?
Yeah. But this Walker-Wang model gives you a way to present it as a 3D commuting projector model. So the question I have is, what does this have to do with, first of all, is that true? Is that the case? Is that the only way to give a commuting projector construction for these? And if so, is there any relationship to the framing anomaly?
I can't give you a clear answer, because the framing anomaly, I understand what it means in the continuum. I don't understand what framing anomaly means on the lattice. And for some reason, you wanted to ask your question on the lattice, because in the continuum, it's really straightforward to answer your question and to write both the bulk theory and the boundary theory for U1 level K. Right, it's straightforward to write the Lagrangian for U1 level K, and it is U1 level K. And also write the continuum theory that this is the boundary theory of. That's also straightforward. So I think for some reason there's insistence here on using a lattice, and the lattice puts all sorts of constraints on you, which are not intrinsic. Now, when you come to discuss more subtle things like the framing anomaly, it's really orthogonal to the way of thinking in terms of the lattice, because in the continuum, the theory is topological. Naively, it's independent of the metric, but in fact, it does depend on the metric, and that's what the anomaly is, the framing anomaly. On the lattice, you have a lot more, you put in a lot more information. You have some kind of, you don't have topological symmetry. You decided where the lattice sites are. You don't even have scale symmetry. So the framing anomaly is a more subtle thing. And therefore, I don't see how you can even address that question. And honestly,
for instance, there was some works recently that studied the question of whether you can have a sign-free lattice model, a stochastic Hamiltonian, something that would be accessible by Monte Carlo for these non-abelian phases. Even abelian ones like double semyon, it was shown that you can't have it. But for these non-abelian ones, the way it was, or for these chiral ones, the way it was proved was by thinking about what happens to your lattice when you change the topology of the lattice in a way that you're sort of imitating a Dane twist. And you can argue that if you have one of these sign-free models, then there can't be any phase associated with that, which means that you have framing independence. So there's some kind of, obviously it's not the same thing, like having a framing or
the story
on a
might be
lattice.
more subtle, because the story cannot possibly be the model is topological, does not depend on the metric at all, and then there's slight dependence on the metric through the framing anomaly. This is what happens. This is the story in the continuum. Naively, it's independent of the metric, but in fact, it does depend on the metric slightly through the framing anomaly. Hence the word anomaly. Now, on the lattice, this cannot possibly be the story. So there might be something else that captures the same coefficient, the framing anomaly coefficient, C. There might be something like this on the lattice. Honestly, I don't see what the lattice buys you in this case. If your goal is to put it on the computer, then maybe it helps. But as far as I can tell, the continuum description is a lot cleaner than the lattice. Now, the lattice could be useful if you don't know what the continuum description is, or you're not sure how to treat the continuum description because it's too subtle, or you don't know how to compute it. You have to put the system on the lattice. But other than that, now you don't try to put the harmonic oscillator on the lattice because you just hold the system. The same thing for the hydrogen atom. And I don't see why we should put the harmonic oscillator on the lattice.
Well, I think it more has to do with like these quantum simulators, which are naturally lattice systems. You know, eventually we'll be able to make things. Of course, there are like, you know, 2D, like quantum Hall is like a continuum system, right? But you know, some systems we'd like to make are naturally lattice systems. So I think it's interesting for that reason.
Or if we want to make a computer out of these things rather than put them on the computer, like we need.
Yeah.
In all the simulation settings, like AMO kind of experiments, it's always some discrete set of qubit degree of freedom, right?
Maybe for the purpose of making like a purely theoretical question, there's some way of saying that you have a particularly nice UV limit. Like it's special to come from a lattice model, I think, just because you have a UV that with finitely many degrees of freedom per unit volume.
Well, I think it's even better in the continuum because you have 0 degrees of freedom with short distances.
Yeah, that's true. But there's something more local, like somehow in the I want to say something about entanglement. The fact that you can have product states is important as well.
But not yours.
I think you want to embed. You see, you can put the same continuum system on the lattice in many different ways. And what the continuum theory has is only the universal information in the lattice theory. All the stuff that you're not interested in is gone. So going back to the lattice, it seems like a step in the wrong direction. Unless you have good reasons to do that. You're not sure what to do, you want to put it in the computer and you need to calculate, etc., etc.
Nati, sorry. Do you agree, quantum field theory, a lot of them rely on human souls? Not everything is well defined. I think even mathematicians probably agree.
Yes.
Even Young Mills, so you want Maxwell theory, gauge theory, if you want to sum over all the gauge bundle and with gauge connection, I think even the partition function.
I don't think I agree with that. I think the free field theories are well defined. The free field theories are well defined. Even mathematicians are happy with that. The Chern-Simons theories are well defined.
TQFT, yes, TQFT, yes. You know, those are good examples. But I think I talk to mathematicians. Even they are not happy with Maxwell, or just U1 gauge theory in 4 dimensions. Let's say, not even say Young Mills.
Is that right? There are some formulas for them written by mathematicians.
Yes,
I'm not a mathematician, but what's the problem?
Well, I think
just to put it in perspective, non-abelian gauge theories are much more complicated because they are interacting.
Yes.
In the perturbation theory, they are now rigorous by a mathematician.
Yes.
No,
but
so if the interacting theory, perturbation theory is rigorous, the free theory is clearly rigorous. Yes, I don't see what can possibly be wrong.
Well, but can one compute the partition function of Maxwell theory on some 4 manifolds, that given any 4 manifolds, and maybe also specify the gauge bundle you want to sum over?
I thought the answer is no, isn't it? I'm not the person to answer that, but I thought the answer is no.
I talked to maybe Yao's collaborator, and who is also familiar with the.
I would be curious to know what you cannot compute in free Maxwell theory.
Well, maybe
that's easy. That's that easy. 1 + 1 dimensional compact boson. That's a free theory. You need to put it on the lattice or not. The continuum theory. The lattice model is a different system. But if you're just interested in this system, I know the partition function can be worked out on any manifold you want.
Yeah, I think some of these theory probably study maybe in this the 2 volume of this QFT for mathematician, this IS2, this 1 years, that they have good lectures. I'm not sure in which standard these are not well defined, but anyway, I just talked to a mathematician who also familiar with this 2 volume, but he thinks even the 4D Maxwell gauge theory is not well defined.
Okay.
We can still compute things, but not sure whether this path integral partition function can generically determine. Maybe there are divergence or some other things that we don't know how to control them. I guess that's vaguely what I feel that the way it is. But I think the perspective for putting on regularization is still it's still good control because computer can read those data.
No,
but
there are advantages to doing that. And I'm not, don't misunderstand me. I love the lattice. Things should be put on the lattice when we can. But there's a clear goal in mind, and that is to either perform calculations that you cannot do in the continuum. For example, people put QCD lattice on the computer because they are interested in the spectrum and we don't have another way of doing it. That's great. Also, we get insight when the model is complicated by doing perturbation theory around various points. There are also other situations where we need the lattice. But when the continuum theory is completely solvable, I don't really see what we gained from the lattice.
That I agree. I think QFT has more unifying organizing principle.
But it's also easier to compute. It's not sometimes it's conceptually it's easy, but computationally it's hard. Sometimes it's the other way around. But as far as I can tell here, both conceptually and computationally, it's easy. And it's rigorous.
Well, Nadi, it's also, I mean, some TKFTs are, I mean, like some state sums, trivial. I don't know, you can probably define it without lattice, but the most natural way to define them is to use triangulation.
Right.
So,
no, I have no problem with these.
Yeah.
I have no problem with this system. That's exactly where I think everything is fine. I agree with you, and I think my friend Wang would also agree with that. But for the particular examples here and many others, I don't really see the advantage of the lattice. Maybe there's an advantage, I just don't see it.
Well, I think in this particular context, it's easier to think about lattice because there's a connection to the quantum computation to be made. But I probably agree with you that the physics is described by the continuum theory very well. Although I still have to use the lattice to think about continuum theory, but that's not a problem of the continuum theory.
For these particular examples, I think the continuum theory is really simple.
You mean the B cut B?
Yeah.
Right, but in general, yeah, I agree. Yeah.
There can also be a curse of that simplicity. Sometimes I find myself going to the lattice just to, make sure I'm not confusing myself.
But then do you put it in the paper or do you just write the continuum in the paper?
That is the question, right?
But maybe for the third bullet points on generalizing the non-abelian premodular category, maybe Walker-Wang would be easier. I don't know how to do it.
That could be the case. That could be the case, but.
Well, I wanted to ask Dominic, you mentioned that in some cases gauging the one-form symmetry in this modular case. You were saying that something about that is not as interesting as you expected. I wonder if it's because when you have this non-degenerate quadratic form that somehow the symmetry is like already gauged, like all of the dual operators are anyons are already in your theory.
Yeah, exactly. Yeah, I think that's the way of saying it. Basically, you go through the exercise and you're like, I just found the same theory.
Yeah, it's self-dual, right?
Exactly, yeah. But I mean, if you say the words like, oh, I can condense some abelian anion that's not a boson or fermion, it seems before you do it that it would be interesting. Anyway.
Mm-hmm. Yeah.
But yeah, maybe that's another example of it. Like it would be more obvious if you if you just wrote down the field theories in the first place, you wouldn't have to do the exercise. But anyway.
Yeah, exactly. It's because of this b squared form that you can sort of complete the square when you add, say, ab. You complete the square, sum over b, you get a squared. But is it also a self-duality of the boundary theory?
Yeah.
Okay, that's interesting.
I wanted to ask a question about the gauge Walker-Wang Hamiltonian that you wrote down. So I'm actually very interested in the these transparent objects that you have, where, if I understood correctly, there are things that don't have topological spin. Like if you insert these loops, then like we sort of don't see them in a theory. So I'm just wondering, like, if it's the motivation for writing down those terms in the gauged Walker-Wang Hamiltonian is to sort of make the theory see these transparent objects. Is that the right way to go about thinking about these things, or?
Yeah, I think I agree. So like exactly before in the pre-modular Walker-Wang, they're just some bosonic or fermionic line operators that are symmetries or of the ground state. But then we basically want to promote them to being seen or causing some energy penalty that goes like their length. So then what the gauging does is just ties them to the domain wall of some surface degree of freedom we put in. So if they break this property that they're tied to the surface, there'll be an energy penalty that's going like the length of where they're not tied to the surface. Exactly.
I see. I've also seen these what are those? The cubic terms. I think I've seen them in Yero models as well. So like there's, I know Walker-Wang is sort of like a special case of the Yero model where you just turn off the G, I guess, or rather it's based on two groups. So in two groups, like we have sort of the group of one morphisms and also the group of two morphisms. If we just turn off the group of one morphisms, we sort of get the Walker-Wang model. So I'm just wondering, like, is there a way to, maybe there's a way to think about pre-modular categories in terms of like a special case of a two group or a categorical two group?
Oh, yeah. Yeah, thanks for that question. Actually, I think I missed this reference that would have been good to include, which is some papers of Ryan that I think explain this. So for these examples, that should be true. Basically, these models and the gauged ones should be like the two group models with the group part trivial. There should be some exact correspondence there.
Yeah, that'll be interesting to see.
I think
that's just for the abelian case, right?
Yeah, for the abelian case, sorry. But this is in one of your papers, right, Ryan? Like, or maybe there's a paper by Clement Delcamp, I think, that explains this, just how to just really explicitly map between them.
Okay.
Well, yeah, I had one other thing, actually. I just remembered that I wanted to say in defense of like, why did I bother looking at gauging the Walker-Wang? It was actually one thing I liked about this was I have these models, these models that Sean Sui came up with a certain subclass of them. So I think we don't fully know what all of them do, but a certain subclass of them exactly just come from gauging these Walker-Wang models. So it gave some way of understanding this subclass in quite a simple, well, emergent, at an emergent level, the properties are simple, even though the model's a bit messy. That was another nice thing of seeing the result of gauging these things.
Great. Thank you for the very interesting talk.
Yeah, thanks for sticking around.
Sorry, I just have a quick question. So you mentioned in some case, after the gauging, the series is self-dual. So I'm wondering what's the condition for this happen? I
think it's non-degenerate. I mean, the theory of the lines is always self-dual, but if you have some degeneracy in the braiding, then it'll go from, say, like a trivial SPT under these lines to a topological order. Whereas if it's modular, then it's always self-dual. It's always SPT. Yeah.
But for the one-form Z2 SPT, I heard that the n equal to 1, the level 1, after you get the one-form symmetry, is dual to the n equal to 3, the level 3 of the Z2 one-form SPT. Can you comment on this?
I think, so that would be like semyon anyons in my way of doing it.
Right.
Sorry, Yuan, is that semyon and anti-semyon?
Right, yeah. So I think in Xiaogang's paper, in the one form, it's classified by the Z4. So it has n equal to 0, 1, 2, 3. I think n equal to 1 label is dual to the n equal to 3 label after getting the Z2 symmetry.
Maybe the way this gauging is defined is different. The way I guess I was doing it, the new, stay on the boundary, the new sectors are defined by like the representations of the old ones. But if you look at the sectors defined by like the semyon lines braiding, they define semyons again, not anti-semyons. So that was why I would say it was be semyons again.
Okay.
But maybe, yeah, maybe there's slightly different definitions or something.
I see. Thanks.
I guess if you just applied a time reversal to the whole thing, it would switch it from 1 to 3.
Well, I think one way to think about why it goes from 1 to 3 is that if you gauge the Walker-Wang models with let's say the p goes to 1, then you will get p goes to -1 because when you complete square, you need to minus something, right? And that turns out to be -1, and -1 is equals to 3 mod 4. So that gives the duality between 1 and 3.
Yeah, maybe I'm missing this because I'm kind of going to a dual lattice and there's some choice of like direction which would flip between 1 and 3, right? I might be making this choice of direction in a flipped way.
Yeah,
to be consistent.
But in the continuum, it's clear that 1 is to -3. Oh,
yeah, okay. Let me go back and check, and maybe I've accidentally flipped some direction. I'm calling it the wrong way. Thanks.
I'm going to stop the recording. We can keep discussing though.